Good morning, everyone. I think it's time to start with the second day of the annual meeting. For this day, just to remind you that in the afternoon, the 16 hours, we will have the General Assembly, where we have the announcement of the next Vice President and also other matters that we have to discuss. So please try to connect to that. And for today, we will start with, I think I see Aurora connected already. So we have an invited talk by Aurora Courtois that is going to discuss about the hadron structure and in particular about some partial status of the experimental and theory efforts in this area that Aurora has been working for some time. And I think this is the best expert in Mexico to tell us what's happening in that area for us. Aurora, are you connected?
Yes, I am here. Do you hear me?
Yeah, I can hear you very well.
Okay, I'm gonna share the screen, I guess, right?
Yes, please go ahead, and I will tell you 5 minutes before the end of your talk, just that you wrap up everything.
Okay, sounds fine.
Thank you very much. Please
okay,
go ahead.
Let me. Okay, so I think first you have to stop sharing your screen, right?
Yes.
Okay. Okay, I'm sharing the screen, and let me see if I can play it now. Okay, can you confirm that you see?
Yeah, we see it.
Okay,
we see
wonderful.
Well.
Okay, okay, so now I can start. Okay, so good morning, everybody. It's kind of early for some of you, I guess. And thank you very much for the invitation. So first, Ivan asked me to make a summary of status of all QCD efforts. And I told him that it was impossible for me to do that, and in such a small, well, no, it's 40 minutes, right? We cannot do that, and there's a lot to be covered. So I'm just gonna cover my partial status, so partial in two ways. So it's a part of it, and that's my point of view, right? So I hope I won't forget anybody, but okay, here it is. So so first, let me just start with QCD in hadron physics in Mexico. It covers much more than what I'm going to talk about today, because as I said, it's other things to be covered. But so basically, then you can see these triangles, the pillars that we have here. So there's spectroscopy, extreme conditions, PQCD, structure, and other things. And to cover those at least four and other topics, we have also four different points of view that are complementary, which is theory, phenomenology, lattice, and experiments. And I think we have a bit of everything here in Mexico, and I just cite a few experiments that are relevant here. There's something that is really important that's really growing now in physics. There are collaborations, and so there are collaborations. People think about collaboration as coming from experiments, but actually what we have now is that we have a lot of collaborations coming from phenomenology. And for example, we're going to have a talk about JPAC, I think, right after me. And there's also this collaboration between phenomenology and experiments. So I think this growing trend of collaboration is really helping science actually to grow and to go faster. And that's something we have to push for. Okay, so that's the abstract of my talk. That's just in few words, if you have to remember something. Well, that's not just that, but just I'm going to talk about pion and proton. And I just want to mention that that's my partial choice, and I will only talk about that, right? So there will be time for other things in the future. Okay, so let me go. I didn't call it outline because I'm not sure I'm going to do it in exactly that order, but it's an abstract. Okay, so basically, if you keep this in mind after the talk, I would be happy. Okay. So so basically what I'm going to talk about is hadron structure. What are the objects that define the structure? And I will give like a short status for the proton. And the main improvement in the last years has been basically the inclusion of lattice data, lattice calculation in the game, okay? So you have PDF updates, lattice improvements, and that's the most beautiful marriage ever. You will see it's getting like really interesting here, okay? And there will be also some phenomenology prospect for the proton. And there's this exciting news about the EIC. I'm going to mention a bit. There will be JLab, maybe LHC spin and other things. And for the pion, it's kind of moving too. So there's there's FENO for the pion too. There will be some at EIC, JLab as well. And there's a new proposal for Compass++, and there will be Compass as well for the pion. And as most of you know about it already, especially we have colleagues working on the pion a lot here in Mexico. The pion is a really beautiful object that is the best elegance that you can think about in theory. And there's also a lot of lattice coming into game. So you see this kind of, it goes in parallel for pion and proton in different points of view, but then you have the theory, the fits, and the lattice and the experiments. And that's really exciting because we can now cover the four aspects for the two hadrons. And that's really exciting. Okay, so let me start with a structure. So here you see a few, just showing examples of processes. There are many others, but this is mainly DIS type of processes. So I start from the left with inclusive processes. I cannot use a mouse. Okay, inclusive processes. Okay, and you can see when I see the proton, there's nothing or the arrow. It means that's unpolarized or polarized in one direction, right? So in that case, you can have polarized, or you can have sometimes it can be totally polarized too. Okay, so inclusive processes is on the left hand side. In the middle, we have like semi-inclusive processes, and you can see that you need at the end we detect at least a pion or something else like hadron. Okay, and you also have exclusive processes in which you detect all the final state particles. Okay. And once we have those processes, you can see they are like dashed lines, and those dashed line corresponds to what we would have through factorization theorems. Of course, my plots are just sketch. You know, it's just it gets more and more involved in PQCD, but it just tells you like where you have the blobs, the blue blobs, you would have non-perturbative objects that are defined through these factorization theorems, and the definition of those that come from how you factorize them and how you have to define them from PQCD. But they are non-perturbative, and then I will just go to the division after that, right? And then all the rest, all that is not this blob of things, the hard cross-section and the corrections, they come from PQCD too. Okay. So this in principle, we can calculate the hard cross-section and the corrections, and what we need to understand the hadron structure, what defines it are the blue blobs, okay? So those blue blobs, they have all different names according to how they are defined, and also they come with the Lorentz structure, right? So so there's a game with the spin structure, and from those spin and the vector at hand, you can build different Lorentz structures, and you have different objects. So the most known, the best known PDFs is what I call here pattern distribution function, which is a collinear PDF. And it's mainly known from inclusive processes that you can see here. So, and there will be DIS, but it can also be something else like proton-proton. You can have different things. You can have many hadron collisions, and you have this unpolarized PDF that depends only on X Bjorken that it's mentioned here, and on the scale, on the hard scale here, which in the case of the DIS is basically the virtuality of the photon, okay? And if you go to semi-inclusive DIS, for example, you would have what is called TMDs, which is transverse momentum PDFs, and they depend also on the intrinsic transverse momentum of the quarks. And you can also have something different that are collinear chiral PDF. So if you want to have chiral objects, you need to have a partner that is chiral out too. So you need at least two objects, right? So you can, the whole observable is chiral even. And in that case, it would be a fragmentation function, okay? And if you go to exclusive processes, then you have GPDs, which are generalized PDF, and they depend on more variables. And in that case, you can see here, to set an example, but then you can also have, that's maybe the most general, but you could have, actually you could have a photon, but you can have cases in which you have a meson production. And this meson production actually is described by a distribution amplitude here. That is still another object. Okay, so this is like an idea of a few objects that we have. So PDFs are like 1D, PDFs and distribution, they're like one-dimensional tomography, they would call it. GPDs are 2-dimensional tomography, and TMDs are 3-dimensional tomography. Okay, so we can access the different pictures and different views on the hadrons from those quantities. Okay, that's basically that. So when I talk about 1D, it's just collinear PDFs, and then multi-dimensional will be TMDs and GPDs. Okay, so so now we want to have a definition of those objects, and I put 2 leading twists because they are also different. There's an ordering too here, so even if it's non-perturbative, we have a different parameters to order the distributions here. So basically, what you have here, you have like the quarks that are sandwiched into between proton states or pion states, whatever you have, and then you can define the leading twist 3 PDFs that are here. So you have F1, G1, and H1. And I call F1 the ubiquitous and polarized PDF because that's the best known and it's almost everywhere. Okay. The helicity PDF, that's the blue one that comes with that's to the spin of the proton, and the transversity. That's the Carolod one. That's a bit more tricky. And then, as I said before, and it's important, so those are defined on the light cone through so they're defined through those factorization theorems, and they depend on Birkenex, which is the fraction of momentum carried by the active quark. So there's one strike quark here, there, and it carries this fraction of momentum of the target. And then, of course, so you can take those objects, so you define F1, and you can have F1 in one process, another process, and it should be the same object, right? So you can take the same definition and do that. And the way you connect, again, and those normative objects to the cross-section and to the observables are through this factorization theorem, just to make sure that it's clear, okay? And those, of course, are evolved in PQCD thanks to the Glapp evolution equation, right? So so we know to evolve it from one scale to another scale, and that's extremely convenient. And of course, I didn't put a scale there on the slide, but it's there, okay? So now the status of those PDFs. So something that is worth mentioning is that so they are non-perturbative. We cannot evaluate them from first principle, but we can do many things about that. So people can evaluate them in models. You can do different things, but one of the most convenient, realistic way to get them exactly is from data. Okay, so you do those feeds, global feeds of data, and you extract those PDFs from the data. So this involves, of course, theory and experiments. So it's this beautiful combination of the two, and you can see the difference. And as it goes, so the unpolarized is like the best known, as I said, and you can see that this recent feed by CTEX, CT18, they're on the left hand side. And I mentioned there are at least 3 groups, and there are probably others too. Okay, and you can see the helicity PDF in the middle of the slide, and you have also different groups working on that. And there's the least known, the baby PDF. It's a transversity where you have on the right hand side only 2 collinear feeds. And as you can see, we have one in Mexico here, and we are really proud of it. Okay. Okay, so that's the status. And if you want to see the status of this PDF, there's a reference which is we call PDF lattice all through the talk, and it's a really good reference. It's a status report about the efforts from the PDF feeds and PDF from the lattice. Okay, so do not hesitate to consult this document. It's really interesting. Okay, just to start with about the unpolarized PDF, which is the one that everybody think about when we talk about PDFs. So well, first it is started a long time ago. So the first feeds were done a long time ago. It has reached a level of sophistication that is impressive, okay? And that people doing the feeds of the other PDFs who would like to go there at some point. Okay, so we just take it as an example, and we're gonna learn from them, okay? So so as you can see here, there's a plot of the ratio of PDFs with the error, okay? So there are still errors at small and high x, okay? But there's also a consensus of how to bring the PDFs together. So I mentioned 3 groups. So those 3 groups, gather information, and they decided on recommendation for the LHC, and then you can consult also the PDF for LHC manual. I think there's a paper. I'm going to give the reference in a few minutes. And so that there are a few things that we know about those PDFs. So you have to think that even though they're non-perturbative objects, we have constraints from first principle. So first you need to have positivity of the cross-section, which involves positivity on the PDF itself, right? Then we have counting rules, and we have momentum sum rules and charges, okay? So those things have to be in a full field. They respect it all after the feeds, during the feed, and all those things, okay? So those are some limits to test your framework and your benchmark for the PDF feed. And what is the difference between different sets is the way people treat the error. So first, you will have a lot of data, and I will show a plot in a few slides too. They have large data sets. So that's wonderful. They can play with it in more easily. And so there are some missing, there are errors coming from missing higher orders corrections. And there are errors coming, of course, from the fit itself, the way you fit it. So, and there's error coming from the way you parameterize. Because when you have to fit a function here, and it depends on X, basically, you have to find a functional form and the parameterization, and the way you do that will influence, of course, the result of your fit, right? And then that's what is shown on the right-hand side. When you see all those green curves, there are different functional forms used for the fit. And you can see each of those will have different error, of course, but you can see that they kind of span the error band that you already have, right? Okay, and if you want to know more about how to do a good fit and how to test your framework, there's a reference there that I also suggest that you consult it. It's really interesting. Okay, so just to mention, because that's a question I've been asked last week, and it's recurrent questions. So for example, as PDF, yes, they are really known, but they come with an error. Okay, so I cited an envelope or central value in an error. But if you guys in whatever calculation decide to use PDFs, please keep in mind that it's not an absolute value. Okay, it comes with an error. Okay, and you can see it. Okay, so there's a recurrent question: which PDF set to use? And then I'm not the expert for those ones, so I would just go tell you to go to this PDF for LHE document and to decide by yourself. I think it will depend on what you want to do with the PDF. Okay. So so now that we've talked about this unpolarized, let me talk about the transversity PDF, which is the one that I like probably the most so far. Okay. So same thing. So it's a chiral PDF. So it means that it has to be coupled to another chiral partner in the cross section to make the full observable chiral even. Okay. So it means that it will never be by itself. It is always combined with something else. Okay. And it makes the fit a bit more tricky. Okay. Because you need two different objects. And then we have the same thing as before. So the X Bjorken is the momentum fraction, so it can only be included from 0 to 1. And then you have the endpoint behavior, which means that it's same for the other PDFs too, that it has to go to 0 at X equal 1 and X equal to 0. And you also have some positivity bounds. And in that case, this bound is called the Soffer bound, and it means that the absolute value of this transversity is smaller or equal to lower or equal than 1/2 of the sum of the two other PDFs. Okay, so that's really interesting. And here, as I said before, the choice of functional form is actually a crucial step, and it's a statement about physics. Okay, the way you choose the functional form is like talking about politics, right? So you say, okay, that's the way I choose it because I believe in this, and it's the way you choose the physics you want to put into your fit, right? So, and of course you want to respect all those points that I mentioned before, the Soffer bound and all those things. So the explicit the first choice is to take it explicitly. So you take a functional form that includes this Soffer bound. You multiply that Soffer bound by a function that goes from -1 to 1, okay? And then you make sure that you're inside, okay? And there's also this function f, capital F, as this typical shape of x to the alpha y minus x to the beta times another polynomial, and it comes from some first principles, kind of, and also the wisdom of previous fits. Okay, But what would happen if you do that? And you will see on the right hand side, that's an old fit we did like 5 years ago, I think, maybe more. And what you do that, and when you see that, and you will see that sort of the positivity bound, the suffer bound is the blue curve. And what you see immediately, especially for the down, which is on the lower plot, that the fit sticks to that bound. So it saturates the bound. And that's kind of annoying because it means that the fit would like to go down, actually, right? And so you would think, okay, there's something going on here, and we would like to improve that because we're losing flexibility here, okay? So that's actually what we've done we want to increase this flexibility in this fitting procedure. And that's what we've done with the students, 2 students at IFUNAM last year, and we wanted to do it differently. We checked actually, so we took the data and we analyzed them in different way. So we first analyzed what is the probability for the bound to be correct given the data. And then we basically weight the objective function of the fit thanks to this this first analysis of the data, okay? Then we take the statement of the functional form, okay, and we make the fit 200 times, okay, that's the bootstrap. That's a bit more complex, but that's basically that. And then of course we want to fulfill the first principle. We want the PDF to be 0 at x equal to 1, and we want it to go like 1 minus x to some power, and to be somehow inside the statistical error of the bound, right? Okay. So the way you can do that, you can constrain your fit using the language multipliers, and then you get these kind of things, right? And then you can see that on the right hand side, so the upper panel is U valence, and the lower one is D valence. That we have different fits, different. Well, we have the 1 sigma and the 2 sigma results, and you can see the different behavior at large and small x, okay? And you have the positivity bound too in gray, okay? So, and I'm gonna show a comparison with the others in a few minutes too. So in that way, you can see that we don't stick to the bound, and it's for the D balance, actually we go a bit outside the bound, but it's still reasonable due to the statistics, okay? And there's more flexibility to that. So, and that's a plot I showed before, but I'm going to show it again. So if we compare now, so on the left hand side, so that's still, so we are the blue, so the Mexican group is the blue, and then the Pavia groups, that's the one I mentioned before, so Radice and Baqueta, they are the pink ones, and then you see that they really stick to the bound, and while we are a bit more free, right? And you can see that the up valence is kind of compatible, and the down is compatible where there are data, right? So when you have this huge error band, it means we don't have data, okay? Basically, that's what it reflects, the flexibility of the fit. So, for the case of the transversity, that's interesting because we have actually, you can have the tree, same for the unpolarized, for the helicity, but I just showed an example here, that you can have PDF, TMD, and GPDs. So the TMDs, if you integrate over this transverse momentum of the quark, you should get in principle should get back the PDF, and the GPDs, if you don't have any momentum transfer from the initial and final state, then you should get what is called the forward limit. You should also get the PDF, and so that's interesting because combining the tree of the 3 points of view, you should get a common description of in those limits, right? So the only 2 Konya PDFs we have are on the left hand side, okay? In the middle we have this TMD extraction, okay? So that's the rectangle here. So on the top, that's the okay. And then on the right hand side we would have the GPD, okay? And combining the 3 of them, that will be in the future. We would have this wonderful picture. So it means that you can compare basically what you get from one and the other. Okay, not that you can fit all of them together. Okay. So now going more into multidimensional pattern structure, there's a lot of phenomenology going on too. There have been a lot of global things, including TMDs, and the one that I just mentioned here. Okay, the one in the middle, Camarota and company, they are called JAM20, okay? And those guys, they make global fits, including TMDs and stuffs. And there are also like more focused fits of TMDs. So there's the Pavia group is doing the unpolarized, and recently they had one about the polarized, these transversely polarized TMDs. And I just put here the expression, and that's the expression for the unpolarized quark inside a transversely polarized nucleon. I think I can see the proton here. And this is a combination of the unpolarized TMD for the proton and the Sieverts function that is here. Okay, this F1T perp is the Sieverts function. And you can see, so you can see on the right-hand side is this, this beautiful plot where on the top panel, so you have the U and the D. So, and then you have this polarized, okay? And then you can see what happens when you when you have this the Sieverts function. So when you have these effects of the Sieverts is shown on the bottom plot. So you will see this distortion of the density in the K plane. Okay, transverse plane actually. Okay, and then of course to do fits of TMDs, it involves a lot of theory too, and there'll be a lot of efforts from the theory side. So you need to have TMD factorization and evolution. And if you want to see recent development of all those things, there are papers by Collins, Rogers, Shimemi, and Vladimirov, and then you can just check there, okay? And there's also application to phenomenology from another point of view, which is pion Indo-Australian, and I will just talk about it a bit later, okay? Because you have the pion and the proton together. That's really interesting. Okay, so now, lattice in PDFs. So I mentioned updates from the PDFs from the feeds point of view, and now we want to know what the lattice can do. So the first thing you can get on the lattice are the moments. Okay, so I just give the definition of the lattice of the moments, Mellin moments. They are projections on X, right? Basically. So we go from the 0th moment, and you can go 0, 1, 2, 3, you can whatever you want to go. And there's been a definition of the, okay, I forgot to say that. So there's said PDF lattice. So there was a first white paper that was published 2 years ago. That's called PDF lattice 1. And now we are PDF lattice 2, which is the one I mentioned before. Okay, so the benchmark quantities were defined in the first white paper. And now the second white paper is including more definitions. Okay, so it's going to multidimensional PDFs. Okay, so there are some benchmark quantities for the unpolarized, for the polarized, as you see here. So basically, you would have the second one from the helicity is GA, that's the axial charge, and the one from the is the tensor charge. Okay, so those are the ones that can be evaluated on the lattice and from phenomenology too. That's what I call benchmark quantities. So in that document that I mentioned here, so this PDF lattice 2, okay, they are like a version of the flag, like the flag tables, but that include both phenomenology and lattice all together, right? So you will see plots like this and tables. So I just copy paste part of it, okay? And so on the left hand side, you would have this unpolarized, okay? And you see on the tables that you have the lattice values and the global fit values, okay? And in the middle, you have GA, okay? And the same thing. You have lattice and the global fit. And you see that they kind of, they're in a good agreement, okay? And the new one from this new report is the one on the right-hand side, which is GT, the tensor charge coming from the transversity, okay? So, so you see that you see first that from phenomenology we have the green curves, the green points with error bars, and we actually have big error bars, okay? Except the JAM. The JAM includes somehow lattice in their data, so there's something different going on. And you can see that we can be in agreement with the lattice for GT, but it's still kind of it's not the perfect agreement, okay? So I think that's worth mentioning here. And I want to talk about this just for one slide, okay? And that's an open question. So it's possible to get an agreement between lattice tensor charge, this isolated tensor charge, delta U minus delta D, if you have a more flexible functional form. So that's a plot here that I modified myself. So there was the different plots, and we see that in Mexico here is the the left point, and I put an arrow there, and we kind of agree with that, okay? But there's something that is really interesting that I haven't shown, but you can also get delta U and delta D separately, okay? So even though you can agree with the lattice to 1 sigma or even more than that, and you can, what is interesting is that you can see delta U. So the lattice would be Alexandru, okay? There's how do you call it? Is it magenta? A magenta point. And you can see that it's really tiny, right? That there's almost no error. But then most of the phenomenology is actually really far from that, right? So delta U is much smaller from phenomenology than from the lattice. So there's something to be understood there, right? So it's the best determined actually from the fits, but it does not agree with the lattice from that point of view. Okay, so there are efforts to be done here. Okay, so the second thing we can get from lattice, and there's been the new developments of the last years, is that lattice can get now quasi-PDF or pseudo-PDF, so there are different frameworks, and they're basically Minkowski version of the Lycon PDFs, and so they can evaluate that, and you can match them to Lycon PDFs. And I want to mention that this matching contains uncertainties, and there are still some challenges that I cannot talk about because I'm not an expert, okay? But it means that even though lattice can get PDFs, they are not yet comparable with the phenomenology PDF, okay? So I was asked also a few weeks ago, can we use lattice for PDFs on the lattice, calculation? I would say not yet, okay? And then you can see, so on the right hand side you have the different combinations for the polarized, helicity, and transversity PDF, okay? And you can see that the lattice still has some wiggles and different things, but globally it's doing pretty well, okay? But so it's interesting to compare with them. So there's something else that you can do, what people call exploiting lattice QCD. So we can use lattice moments to reconstruct or reweight PDFs, and you can use lattice moments as data points, okay? So I show a plot by other colleagues, by Liutin and Rajan, when they reconstruct the GPD H from the generalized form factor related on the lattice. So you can get form factors and reconstruct GPDs. So this kind of synergy and between lattice and phenomenology is extremely helpful, especially where you don't have data, right? In some ranges where you don't have data. Okay, so new experiments. So there are many things to say. So the polarized PDF, polarized, and all this multidimensional distribution function. So the unpolarized, they're almost everywhere. Okay, so they are sensitive to high energy, low, and mid energy experiments, to everything. The polarized PDF, so you need polarized targets, so it's a bit more involved. And so they're mainly relevant at low and mid energy experiments. Okay. And these multidimensional distribution functions, they are much more involved experimentally because you need to reconstruct different momenta. Okay, so you need to see different things to be able to understand what's going on. And so so far it's been mainly low and mid energy experiments. So, and I put here the only good news of 2020, the EIC is going to be built. So EIC stands for Electron Ion Collider, and it seems going to be built at BNL, Brookhaven National Laboratory. And that was really good news. And ongoing, there's class at JLab, and there will be soon, hopefully soon, the whole A is going to have solid, okay? And there's a proposal for LHC spin too. And so here come the arrows, okay. So you would see the unpolarized is going to be, well, it's almost everywhere, right? But the EIC is going to be interesting for it. There are more experiments at LHC, and the EIC is extremely interesting for polarized and for multidimensional distribution functions too, okay? LHC spin too, and class, it's more like low energy, but it's going to be interesting for all those things too, polarized and multidimensional distribution functions. So this is really exciting times for the community. Okay, so just to give an idea, so that comes from the same PDF lattice document, and that's really interesting because you can see in the same design exactly the difference of data sets from the unpolarized, helicity, and transversity. Okay, so you see, so the left panel is still the unpolarized; they have a lot of data. Okay, the helicity is slightly less. So I think there's a difference of 1 order of magnitude every time you go to the right, and then you see that the transversity is is the poor one. Okay, so we don't have much data. And what is interesting too is this band putting the kinematics, the kinetic range relevant for the EIC. So thanks to the EIC, you're gonna have more data on those in those range of kinematics, especially covering more Q square for the transversity, which is really interesting, and lower X values. Okay. And okay, it brings me to another slide that I borrowed from some colleagues, and I think it's really interesting to see that. Let me explain this slide. Okay, so so the EIC is, people think of the EIC as like a mid-energy machine to test PDF and 3D structure of the nucleon. Okay, it's true. Then I will tell you about the pion too. Okay, it's true. But for people doing feeds, global feeds, what is interesting to see is that there's an impact of lower energy or mid energies to high energies. Okay, so that's an example you have here, and then we explain what is sensitivity. But basically, it shows the impact from the EIC data here, pseudo data. Okay, let's put on the pseudo data, the EIC data on the global fit, and how this global fit will influence the Higgs production. Okay, so that's an example here. So that's sensitivity for the Higgs production. So basically, the Higgs production is sensitive to the PDF, the gluon PDF, and the gluon PDF comes mainly from the scaling values of the Dirac equations. Okay, that's PQCD, and of course, the way you feed your PDF from lower energies influence the gluon PDF, and this gluon PDF, that's what you see here, right? So you would see that the high sensitivity is like in orange and red, and you can see that lower energy here at EIC for this DIS, you can see different processes that we consider here, will have an impact on this high energy. Okay, so this EIC machine will also have impact on LHC physics, kind of. Okay, and that's extremely interesting to see. Of course, this sensitivity is related to the fit, so it gives you a correlation between. It tells you the correlation between the observable and the opposite function of the fit, right? So here, that's interesting. And if you want to know more, I'll put the references there. Okay. Okay, so that was for the proton, and then you can go to the pion too, and there are experiments in which pion and proton are all together, like in this pion-induced Australian.
5 minutes, Aurora.
Ooh, okay. I'm gonna rush to the end. Okay, and then you have the Sullivan process on the left-hand side, and you can also have direct photon production here. So you have some data. Some are old, they're not really precise, but you have data. And you can actually make fits, okay? So there have been recent fits of pion and kaon PDFs. You can see the X fitters and JAM. And there's an evaluated impact of the EIC on the pion and kaon PDFs. And there's a review by Christina Aguilar and collaborators there, and you can check it. And there will be COMPASS and COMPASS ++2, where they will have more data from pion into Australian and antiproton and kaon into Australian. And you can see on the plot that I took from a workshop there that so the EIC will tell us more about small x. Amber will be in the valence region, and GELAP from the valence region upwards. Okay, that's interesting. So we talk about the pion, we talk about the dimension of atomic mass, and we can see that chiral symmetry actually influences the shape of these distributions. It also relates the PDF and the PDA. And I just show this simple example of NGL, when you can see it's just one at the atomic scale, and then it changes with the evolution, right? And there's a strong significance in the endpoint behavior in that case. Okay, and what it means that to understand this behavior that shapes the distribution from chiral symmetry, you have key observables that are pion and kaon PDFs as well as GPDs, and you can have the gluon and pion and kaon, and also pion TMDs. Okay, so I'm just showing here a few examples of two different Schwinger-Dyson calculation there, and you can see that some they compare with extraction of the PDFs from E615, I think, Fermilab. Okay. And you can see the different behavior there on different curves from different approximation of the Schwinger-Dyson evaluation. Okay, So those are recent progresses too. And just to mention, I just have 5 minutes, that is also this synergy between PDF, Pi, and F on the lattice. And there's something that's called the lattice cross-section that's been proposed by Ma and Shu. I forgot to put the reference. And you can actually evaluate this cross-section from the lattice from a model point of view. And that's a reference there, okay? So you take NGL, you only have this harmonic scale as a free parameter, and you can actually fit this lattice cross-section only through the moments of the Pi on PDF evaluated in NGL, okay? And you can see that that is going pretty well, okay? So that's really interesting to see how you can reproduce lattice observable from model point of view in for the Pi, okay? Another thing, I'm gonna rush through one slide, not too much. So Pi and multi-pattern scattering, they're also really relevant here because you can have multi-pattern scattering, and you have more than one active quark. That's relevant for high energy collision. And the Pion, you can have double pattern substitution for the Pion. It's been noted in models and on the lattice too, okay? So you won't have data for a while, I think. So that's interesting to compare those two theoretical approaches from models and lattice point of view, okay? So I'm just gonna show you different things. So if you take one model, you have an NGL, say, and you have two different approaches. There was a paper by Risariola and collaborators, and by people, well, my collaborators and myself, okay? And then you can see that we can check a few things. We can check factorization into GPDs, and we can check factorization into longitudinal and transverse variables, okay? And you can do the same thing for two pattern correlations on the lattice, and you can evaluate that and check the same thing for the factorization here, okay? That's pretty new too. Okay, so the conclusions are the more important thing, so I'm gonna do it properly. So there's an extensive phenomenology for the proton. There are windows for improvement to be covered by new experiments and or lattice, so it's two together. Now we finally have spin-dependent objects entering the game, like the big game. And we also have this multidimensional structure getting insights. And this is thanks to an increased elegance in the techniques we're using to do the fits. It's a collaborative knowledge. So we learn from each other, we collaborate. And also there's machine learning and similar things coming into play, okay? So please have a look to this PDF lattice document. And also there's a yellow report for the IC that is under construction. In particular, if you want to, there's a user group that is open to everybody who wants to join. And in Mexico, so far, we only have about 10 participants. So if you want to join, you can send an email. You can send me an email or to other people that you know are involved in that thing. So for the Pion, what is interesting for the Pion is that we have theoretical approaches that are much more under control than for the proton. And the Pion PDF is now on the spotlight, okay? So that's the big thing. And there's experimental hope to have more data and more things. And we also have now multi-pattern correlation. And what is really interesting for the Pion is that it's on the edge of the transition from perturbative to non-perturbative QCD. And we have theoretical guidance from both sides on the transition. And now we also have the lattice. So that's really interesting. And if you want to know more, you can check the workshops that took place in March and in June. I think they're on Indico. You can check all the slides. It's really beautiful. Okay, so that's the conclusions. And now just joint effort of a community. So now it's basically lattice, first principle, global fits, and data all together. Okay, so it's just not one. One point of view is the 4 points of view have to be taken into account. They are complementary and they all go together, and it's the way to go to understand better physics. Okay, thank you.
Thank you very much, Aurora, for this comprehensive review of this what is going on in the field for this. Questions? We have time for questions. I think we have already a couple of questions at least in the chat. Samuel, could you give the microphone to
Andres, if you want to make your question, yes. Sorry.
Hi, can you hear me?
Yes.
Yes. Yeah, I was just wondering when you said that there is no data to get some specific region of the X of the. So you show some PDFs, and you said that there was no data for that. Have you thought about which kind of measurements can you do to get this data? For example, going to high mass energy or low energy or something like that?
Okay,
Because I mean, there is a lot of chances that many experiments can help you to get rid of this lack of data. I would imagine.
Okay, so I can only talk. Okay, so I won't talk for people doing this unpolarized one. Okay, so I can talk about this one. There will be new experiments. You can see the mass now. So there will be new experiments covering a bit more, as we see here from the IC. So from what I understand from the unpolarized PDFs, and it's also what is shown on those plots, right? So that sometimes, even if you have data, it's not that the fit is always sensitive to all of these data, right? Because so you have, as you see, there are many data, and of course you can improve, and the IC will be one to improve this coverage. But even if you cover more, depending on the process you're having and the flavors you involve, you can only improve some of them, right? You can't improve all of them together. So I don't know exactly. I don't know exactly. So I think. So for this transversity, of course, whatever data it's better than nothing. But here I'm supposed that the experts have thought about it, right? And I understand that some processes give more sensitivity to the fits than others. It's not only the coverage in X in Q squared, right?
So you're saying that you are not limited by the amount of data, like a statistical limitation that you have is more something that you have to think about the phase space and where to look at.
So there are many things. So if I think about transversity, we have different. So you need the nature of the target to have like flavor separation. You have different flavors. You don't have only up quarks. You have up, down, and you can have different things, right? So and here they have more. So here we have only balance, right? So you can have different. And then you need a Q square coverage to get the effect of D-gap evolution. So the good one will become. There will be different things constraining, right? Maybe the gluon and other things are constrained by D-gap evolutions too. And some processes will add sensitivity to one particular flavors and some others not. So it's not just the coverage in X and Q square. It depends also on, I think, on the process and on the target you would have, right? But I'm not an expert on this polarized, so I don't know. But okay.
Okay, thank you.
We are running a little bit late. There is another question by Pablo, so I hope that he can put it on the chat and that Aurora could answer there, so we can everyone look at the question and the answer. Thank you very much, Aurora, for this review.
Thank you.
Let's continue with Cesar Fernandez, which is going to talk about this PC 4312 that was reported by LHCb. Cesar, are you connected?
Yeah, sure. I'm here.
Go ahead, please.
Yeah, wait 1 second. I have to prepare the pointer. Oh. Okay, can you see my slides? It's fine. And you see the pointer?
Yes, we can see it.
Okay, very good. So thank you very much. It's really a pleasure to be able to give this talk in the meeting of the División de Partículas y Campos. So as actually Aurora mentioned, I'm part of one of these phenomenology experimental collaborations that is called the Joint Physics Analysis Center. And what I'm going to show is one of the results that we produced past year about this particular discovery of by the LHCb collaboration. So the first, let's set the grounds of what we are going to talk about. And it's so when you think about hadron spectroscopy, you know, hadrons, you can classify them in mesons and baryons, which basically is boson and fermions. The simplest way to describe a meson, we know, is just as a quark-antiquark pair. And the simplest way to describe a baryon is just as 3 quarks. And this is called the minimal quark model, which works very nicely and actually describes very well the ground states. It provides a classification scheme. And it is, and actually many excited states of the spectrum can actually be very well described through this very simple model. The thing is that nothing in QCD tells you that this is what you should have. Only you should have this. You can have many other options actually. As far as you have a color singlet, that configuration of quarks and antiquarks and gluons is permitted. You can even think that it's compulsory, that it has to be there through some kind of quantum superposition. So for instance, you can have compact pentaquarks, you can have compact tetraquarks. You can have even things like this, like the barium meson molecule. What is this? I mean, think about this guy, this compact pentaquark. Is that you have the strong interaction, the QCD is binding the 5 quarks into one single state, but there's a chance that actually instead of binding, okay, I'm hearing something. Okay, so instead of just binding the 5, you could just bind 3 quarks in one baryon and 1 quark and 1 antiquark in one meson, forming what you can call a hadronic molecule. Hadronic molecules are not something strange. I mean, we are actually pretty used to them, and when they are just composites of baryons, we call them nuclei. So you can also have glue balls that is just gluon. So anything that is a color singlet, it's allowed and can be there. Actually, we should think probably in terms of a state superposition. So yes, a meson is a superposition of all the available combinations. What happens in states that are mostly QQ is just, of course, this first component is the one that dominates, and the rest are basically, you can think of them maybe negligible, maybe, but less important. The thing is that, think, for instance, in the baryons. So the first term is just 3 quarks, but what happens if you start finding states that are not 3 quark states, that they cannot be described as 3 quark states? Then you are looking at the next term in the series. So meaning that this term is 0, and then this term is the dominating one. And think that then you're looking at by looking into states like this one, you're actually looking into finer details of the interaction. So that's what makes these guys really interesting. If you want to understand this guy, the strong interaction. But how can you make a pentaquark? Well, it's actually straightforward. Think about this possibility that you were able to build a JPSA beam, which you can't, but let's think for a moment that you could do that. And you can collide it with a proton. So the JPSA is going to be basically a CC bar state. You're going to have a proton that is going to be UUD. Then if these guys collide and they're going to generate a resonance and they separate, you're going to find a peak in the data. And that peak is the one that is going to be associated to this signal, that it could be a compact pentaquark or something else. So the minimal quark contact of this signal would be these 5 quarks. And that's what makes you try to look for these kind of signals and try to identify. Of course, you cannot build a JPSI beam, but you can build JPSI proton rescattering. And that's what actually people at LHCb have done. I mean, it's just they have studied the lambda V0 decay into JPSI proton kaon, and you build the Dalitz plot. And basically what you see this, for instance, this band here, and also, for instance, this other band, you see this band, and that guy corresponds when you do the projection to this guy here, and you can see a very clear peak. So there's a signal that is happening in the JPSI proton rescattering. You can also have signals in, for instance, in the kaon proton rescattering. This guy is the lambda 1520, which is very, very apparent. But these are just hyperons, the lambdas basically, which we more or less know very well. So let me show you something that we did and we published past year in Physical Review Letters. So we take this signal and you can study just this region. So it's the near threshold, because one of the hypotheses is that this signal you see here, because it's so close to the sigma C plus d bar 0 threshold, is actually generated by the opening of that threshold. And it could be, so if it's so there are several possible explanations for this guy. You can't interpret the signal. You have to understand where the signal comes from. So one possibility is that imagine that you have your lambda V0, and your lambda V0 then is decaying and decays to these 2 stars, these 2 states, the sigma C bar and the sigma C plus and the d bar 0. And then it's a possibility that the d bar also decays to d bar 0 and k minus. The d bar 0 rescatters the sigma C plus, and you get what is called a triangle singularity. This was actually studied by LHCb for the PC4312, and it was regarded that it was not the origin of the signal. But for other pentacores, actually, it's a possibility, in particular for the 4450. Another option is that you have a compact pentacore. I mean, the moment that you have a discovery of a signal, everybody jumps in and they try to basically to explain that signal and with their favorite model. So there's an option that's a compact pentacore. There's an option that is a baryon meson molecule, and there are many calculations. There's another option that is that it's a virtual state. And this is interesting because a virtual state means that for instance, an example of molecule is, think about a proton-neutron scattering. When a proton and a neutron scatter, they could form a bound state, which is the deuteron. But if you look at the proton-neutron cross-section, you can see that it's not the only possibility. You can collide a proton and a neutron, and they can form what is called a virtual state, which means that there's enough strength in the interaction to generate a signal, but it's not able to, this signal is not able to bind the system. So you can see the molecule and virtual state, they both have the same origin. It's the interaction in the near threshold. The difference is that the molecule has a radius, a finite radius, while the virtual state has an infinite radius. So, but still you have a signal. And then you have other more exotic options like the hadron harmonic. So how do you study a signal in the near threshold region? Well, the first thing you start with the scattering matrix theory. So you start imposing things like unitarity, crossing symmetry, and causality, and analyticity, and then any additional symmetry that you want. And think about the following. I mean, when you have a spectrum and you think about what we're used to solving the Schrodinger equation, whatever, you have a discrete part of the spectrum, you have a continuum. That's when you think in terms of standard quantum mechanics. When you do scattering, you have to change a bit the picture. You have to think that bound states now are poles in the real axis. The continuum is actually what we call a unitarity cut. You have an analytical function, and because you have a cut, you have two Riemann sheets. If you have one threshold, the moment you open a new threshold, you have two more Riemann sheets. And resonance become poles in the second Riemann sheet. And those poles are the ones that actually generate your signal. And that basically, and then you have poles and cuts. The amplitude is going to be an analytical function in the complex plane. And because it's an analytical function, everything is determined by the singularities. That means poles, cuts, and these are the singularities that are associated to the dynamics. And you have to do coupled channels because you can produce different things, so on. So for instance, in the case of the PC4312, you're going to have, when you consider the J-side proton channel and the sigma C plus d bar 0 channel, you're going to have four Riemann sheets. And well, basically, you have to start looking for signals for instance, here you can see a pole you have to analyze the data, build your amplitude, and try to find whatever poles you see in the data. The good thing is that because this guy is so close to a threshold, you can do an analysis of just in the near threshold region. And the good thing is that you have a theory for that. And you have a completely model-independent theory under certain assumptions. So the first, that certain hypotheses, which are reasonable. There are three hypotheses that you have to make in order to do a very good, solid amplitude in that energy region. Is that first, that you only have one partial wave contributing to the signal, which is reasonable if you have only one resonance. That the threshold drives the physics, which you can test. And that any other further singularity is completely irrelevant, which can be tested. There's only one caveat. LHCb has provided the J-psi proton projection. So you have no information on quantum numbers. So you don't really know which one is the partial wave that is contributing to the signal. And that is actually controversial. That's something that you have to keep in mind before making a strong statement regarding what you have found. So in the near threshold region, you can actually build this is the theory that you can build. This guy is the partial wave that contributes to the signal. This is the background. And this is the reaction that you are considering. Of course, LHCb reaction is landed with zero decay into J-side proton K minus, but by crossing symmetry, you can put the K. You can change the K minus by a K plus and put it here. You do the coupled channels. You know what the analytical structure is. You can tailor expand, and in the inverse of the amplitudes and the phase space, you can do this, and then you know what the amplitude looks like. So it's basically You're going to have a background and a production piece that takes into account the production, hyperons, and effects due to further singularities. And all of them, you know, they are smooth contributions that are going to be smooth functions of the S-Mandelstam variable. And then you know that you have this, you have some kind of channel coupling. Then you can define the scattering length approximation. You know what the scattering lengths are, and you can actually compute them from this very equation. And if you are in the scattering length approximation, you can have poles on the second and the fourth Riemann sheet, which means basically you can only have virtual and molecular poles. But you can also build the effective range approximation, and then you can have poles in any sheet, and any interpretation is available. So we did that. We fit it with the scattering length versus effective range, and we actually obtained basically the same kind of fit. We obtained the same poles. You can see this is the pole that we get, and this is the pole associated to the signal, this one and this one. Mass is very similar, width is slightly different. And let me show you what the interpretation is. So you have the pole here, which is slightly above threshold, and you can turn off the coupling between both channels. You can decouple the channel one, the J-psi proton channel and sigma C plus, and see what is the movement of the pole. And the pole, if it were a molecule, it should move from here to here. If it's a virtual state, it has to move into this direction. So that tells you that you have a strong hint that first, the threshold is the one that drives the dynamics, is the one that generates the pole, but also that pole might be, it's a candidate for a virtual state. So let me show you some final conclusions. But because you only have the projection, I mean, the current consensus on pentaquarks actually is this one. I mean, if you are a guy who's doing models on hadron molecules, so hadron molecule community, basically the statement that you're going to find in the people who do hadron molecules is that the pentaquarks are hadron molecules. If you talk to people who do quark models, they're going to tell you that the pentaquarks are compact pentaquarks. And if you do hadron harmonia, well, it's the same story. If you do triangles, I mean, I'm sorry, but actually, out of the 4 signals that we have of pentaquarks, basically 3 of them have been ruled out to be triangles. There's only one there. So it seems that the first thing we can conclude is that it looks like the pentaquark, the PC432 dynamics is driven by the threshold. So actually, the opening the threshold is the one that is generating your signal. Is it a molecule? Is it a virtual state? Well, we need further data. We need more information to be absolutely sure of what it really is. This analysis favors the virtual state explanation, but it's not the only one, because at the end of the game, we need to wait for the quantum numbers. We can make a lot of sensible speculation. There's a lot of them in the market, and there are a lot of explanations. But at the end, until you have the quantum numbers and you see that these quantum numbers match a molecule or a virtual state generated by the threshold, you cannot know for sure, and one has to be very careful making any final conclusion. And well, that's basically all I wanted to say. So thank you very much for your attention.
Thank you, Cesar, for keeping this in time. This quite interesting result from the LHCb. Any questions?
Let me check if we have any question. Not question on YouTube.
I got one.
Yes, go ahead.
So Cesar, this is Ivan. So in the 2016 analysis, the first analysis on these pentaquarks, they measure quantum numbers. So why haven't they been able to measure this again?
Okay. No, it's not that they have not been enabled. I mean, the thing is the following. You have the Dalitz plot, okay? And you have the projections. The moment that you want the quantum numbers, what you have to do is to build an amplitude analysis model, put the resonance, and analyze the full Dalitz plot. The thing is that has not been done with the 2019 data, has not been done yet. It's in the works. The only thing that LHCb produced so far are the projections for the people to analyze. And that's why any analysis has to rely on the projection. But it is in the works. And at the end, it should be published at a certain point. Okay. It's in the works. It's been done. I mean, I cannot disclose more information. You know, I'm involved in that, but I cannot disclose more information than that.
Okay, thank you.
Thank you, Van.
Any other question?
Pablo?
Okay. Well, if there is no more question, let's thank Cesar for this this talk, and let's continue with it. Thank you very much, Cesar.
Thank you very much, Edward. Bye.
We continue with Alfredo. Alfredo, are you there? Connected?
I am here.
Oh, great.
Yes.
Alfredo is going to talk about the chiral symmetry breaking in reduced QED. So please go ahead, Alfredo.
Thank you so much. Just let me. Thank you, everyone, for to the organizers for the opportunity of presenting this topic here. We have had this morning very interesting lecture so far, and I will move slightly from this general topic, but we are close enough as to relate the aspects of chiral symmetry that we are discussing, but now in a theory which is has been dubbed in literature as reduced QED, and we will add a Chern-Simons term. And in order to present the ideas and establish the connections with the topic of this morning session, this is the outlook I am following. I will present a motivation, and then I will discuss slightly what this reduced QED theory is. And I will try to solve the corresponding gap equation of this theory within the Schwinger-Dyson formalism and explore the consequences on the chiral transition that we have. And at the end, I will present some final remarks. So the motivation is basically as in extreme conditions in the early universe physics, we have the transition between the quark gluon plasma and the formation of hadrons. And this happens just a small time after the Big Bang, 10⁻⁶ seconds, probably. And what we have here on Earth to test this possibility are the experiments that measure the formation of the quark gluon plasma. And this is encoded in this phase diagram that I am showing here, which basically says that at a strong enough temperature, but a small density, there is a possibility of hadrons to melt down to the quark gluon plasma because of in these heavy ion experiments, a large number of hadrons participate in a small volume, and interactions are enough as to make a heat bath, a medium which has a temperature and a density enough to melt these hadron states into this soup of quarks and gluons. We know from experiments, and we know also from lattice simulations, that at small densities, this transition is a continuous transition, is basically a crossover. But there are also some theoretical models that says that at low temperatures, but very high densities, the transition from hadrons to perhaps other states, even quark gluon plasma, it's a discontinuous first order transition. So in order to reconcile these two scenarios, it has been theorized that there exists a critical endpoint where the continuous transition stops and the discontinuous one starts. And this has been the subject of some interesting proposals to test experimentally, for instance, in RIC, and there are some other proposals in NICA that nowadays there is a Mexican collaboration in this interested in these experiments. And on the other hand, for very high densities, we have the physics of compact stars or other environments where we can test these ideas. But if we restrict this kind of experiments to collisions of heavy ions at the relativistic energy, what we will find is that on peripheral collisions, on top of having this high density and temperature in the medium that provides the conditions for the melting of hadrons, it could be, and it is actually tested, that there is a generation of a very high, very strong magnetic field. And this is because in peripheral collisions, there are nucleons that do not participate in the interaction, and they play the role of currents that eventually give rise to these strong magnetic fields that, by the way, live very shortly. But if you have temperature and density and add the ingredient of a magnetic field, of course, the richness of the phase diagram increases a lot. And in fact, there appear a number of different phenomena that you can test, and they are triggered by the effect of the magnetic field. One of these examples is the chiral magnetic effect, where there is a charge separation of the quarks due to the interaction of a magnetic field of the quarks with a magnetic field in a place of space where vacuum is non-trivial. It has a non-trivial topology, and therefore it induces a chirality flip such that at the end of the day, there is some imbalance of chirality, and this gives rise to this phenomenon. Of course, when you compare the predictions of the signals of this chiral magnetic effect to occur, it's a very suppressed signal, and therefore you can not easily disentangle the presence of this effect from experimental signals. Therefore, what the community has tried to do is let's locate, or let's try to identify what could happen if we move from this environment to other scenarios, physical scenarios, where you can induce the imbalance of chiralities in a different system. And that is the case of this Dirac crystal, zirconium pentatelluride. It's a three-dimensional crystal which has a linear dispersion relation that therefore allows a description in terms of a Dirac equation. What is interesting of this material is that when you have the presence, you put this crystal in the presence of a magnetic field, what you will have is an immediate development of Landau levels. In these materials, electrons are also chiral. They have a chirality that you can use to characterize it. But in the presence of a magnetic field alone, what you would have is that these two left and right chiralities appear in the same symmetrically in the spectrum of the crystal. But as soon as you turn on an electric field, which is parallel to the magnetic field, what you actually do is you generate a chemical potential, and therefore one of the chiralities that is aligned along the momentum of and the spin of the electrons, that already starts being more populated, and the other one, the other chirality, the anti-aligned chirality, is no longer as populated as the first one. And therefore, this is a smoking gun for the chiral magnetic effect being tested in these materials. And this was done just a few years ago in a solid state system that like this crystal. And the question that we have asked ourselves is, can we do that, but in a crystal that is not three-dimensional, but bidimensional? And this is because the physics of graphene has boosted the interest of merging the ideas of high energy physics into the realm of solid state physics. As you might remember, the basic idea of the physics of graphene is that it consists of a layer of a sheet of carbon atoms tightly packed, such that the dynamics of electrons corresponds to a ultra-relativistic Dirac equation, but only in 2+1 dimensions. Now, the thing of studying this system in the presence of external magnetic fields is not trivial, because although you can constrain the dynamics of electrons to a plane, you cannot do the same for the electric field. The electric field simply moves throughout the space without restrictions. But you can formulate the type of interaction where you make an analogy of what you do usually in brain world scenarios. In brain world scenarios, you constrain the fields of the standard model to a brain and allow gravity to move in the bulk. But what you do here is the same analogy, where the matter fields are only electrons that move in this two-dimensional sheet, but the electromagnetic field can move through space, and this will play the role of moving in both dimensions. When you do the dimensional reduction of this to the sheet of the electrons, you end up with a Lagrangian, which is very similar to the standard QED Lagrangian, but in the gauge sector, what you get is the appearance of a fractional power of the D'Alembertian operator, And that has very interesting consequences when you try to analyze this theory in terms of the properties of renormalizability and so on. For example, one of the first things you can notice is that the Feynman rules in this theory change from the ordinary Feynman rules of QED. As electrons remain massless, we will have the same form of the fermion propagator as we have in ordinary QED, or for relativistic fermions for that matter. But for the photon propagator, what you actually have is a softening of the infrared divergence in the propagator. It is no longer 1/q² as we are used to in ordinary theories, but it goes like 1/q, and this softening has a very strong consequences regarding the nature of the interactions in this theory. So what we do, the idea that we are pursuing is try to solve the gap equation for this theory, and the gap equation is the non-perturbative equation of motion for the electron propagator, which relates this two-point function with the corresponding for the photon propagator and the fermion photon vertex through the self-energy that appears here. So the basic idea that we follow is, as we usually do in Schwinger-Dyson studies, is to replace I will come back to this transparency, is to replace the fermion photon vertex and the photon propagator by their bare counterparts. And therefore, what you have to do at the end of the day is solve the gap equation in this so-called rainbow approximation. And in this expression, it's an integral, nonlinear integral equation that we'll have to solve. And you will see that in order to have a non-trivial solution to this equation, you require the electromagnetic coupling to exceed a critical value that has been calculated already in literature to be of the order of pi/8. And so when you have a coupling that exceeds this value, you automatically are able to generate masses for the fermions in this type of systems. Now the question is, what happens if we do a generalization of this scenario, but we include a non-trivial topology to the vacuum? And this can be done by adding a Chern-Simons term. The Chern-Simons term acts as a mass for the photons, but on the other hand, it has the following consequences for the fermions.
5 minutes, Alfredo.
Yes, thank you. It induces two types of mass terms, the ordinary Dirac mass, and there is another mass term, which is in solid state literature is known as the Haldane mass. The first one breaks chiral symmetry, but preserves parity and time reversal, and the other does the opposite. It is invariant on the chiral symmetry, but it breaks parity and time reversal. None of these correspond to poles of the propagator, but you have to introduce some chiral projectors. Then you would have the left and right-handed electrons, and their masses are different because one corresponds to the sum of these two masses, and one corresponds to the subtraction of these two. So you have two fermion species. One is light and one is heavy, and from there you can already start distinguishing the effects of chirality. So the gap equation is basically the same as before. You only have to project appropriately the corresponding fermion species, and the effect of the Chern-Simons term is also observed that the pole of the propagator is shifted slightly in terms of this coefficient theta that corresponds to Chern-Simons. And the solutions for each chirality start looking very, very much the same. Actually, there is a critical value of theta for which one is the exact mirror image of the other. And when this happens, this actually corresponds to the point where chiral symmetry is restored. And we can observe it in this form. This mass corresponds to a chiral symmetry, and the mass would be of the Dirac component of the mass for the fermions. And for each value of the coupling, there is a critical value of theta where the generated mass experiences a discontinuity. Therefore, chiral symmetry in this case is restored by virtue of the Chern-Simons term, but the transition in this case is discontinuous. And this is the same for the Haldane mass. You observe that the transition is also discontinuous. So the final remarks that we have from this work that is still work in progress is that in this theory, we can break the chiral symmetry provided the interactions are strong enough. And the chiral transition in this case, we know is conformal. That means it's an infinite order transition that induces the mass, the dynamically generated mass to obey a Miransky scaling law. The Chern-Simons term adds a non-triviality to vacuum, and therefore two fermion species arise in this theory that allow you to break parity and chiral symmetry provided the critical coupling exceeds this value in terms of the Chern-Simons coefficient. Also, the transition in this case is conformal, but chiral symmetry can be restored in a discontinuous transition. What are the observable signals and what are the predictions that we have in this case? That is something that we are exploring nowadays. And this work was done in collaboration with one of my students, Juan Ángel Casimiro, and friends and collaborators, Ana Julia Mischer and Luis Albino. Thank you very much.
Thank you, Alfredo. I think we have already some questions. So, Salvador?
I think the first question was from the chat. Cesar, no, oh, that was from the previous one. Wolby, you can ask your question.
Yes, thank you. Alfredo, your gauge action looks strongly non-local to me. Are you comfortable with that, or does this imply conceptual problems?
Actually, that is one of the features of this. It's extremely non-local, but the renormalizability properties have been already discussed in literature. So even though it looks a bit intricate, you still can do some predictions with this theory.
I don't see any other questions. Somebody else want to make a question?
Any other question? Or if there is no more question, we thank Alfredo. Thank you very much, Alfredo.
Thank you.
We move to the next one. Giovanni Mejia, are you connected, Giovanni?
Yes, can you hear me?
Yeah, yes, we can hear you.
Okay, I will try to share my screen.
Giovanni is going to talk about the production study on heavy quark-anion in emissions.
Bueno, perdón, justo estaba terminando una charla en un congreso virtual.
So,
sorry, could you mute your microphone, Alfredo? Please go ahead, Giovanni.
So now, can you hear me again?
Yes, very clear. Sorry.
Okay, very good. So as usual, it's very nice to be here and take this discussion with you. Thank you very much to the organizers. So I will talk about some results for CMS collaboration. To be honest, after very short talk yesterday with Jose, we decided to talk here about their two results, but the main of this talk is about the cross-section of the BC2S and BC2S stars. But we want to take your attention in two very new results from CMS about the heavy flavor. I will just, as I told you, I just will do some comments about these results. So let's start with the observation of the BS2S5 decay mode. This is very interesting. We see in previous talks about the tetraquarks and pentaquarks. This is possible candidate to tetraquark, and here CMS do the first observation of this channel, and this is very interesting because you know we can learn about the dynamics of this kind of particles. CMS in this case use two channels. I mean, do the discovery of this. I mean, of the first observation of this channel, but we use has normalization channel design 2S. We will call psi prime, and you can see here in this plot. This is the distribution of the psi pi pi for and kk let's say, psi prime and phi in the channel of the psi prime and phi. And in the bottom is the new, let's say, the new particle, the new channel is the S channel here. You can see. The interesting thing here is in this analysis, CMS made the measurement of the ratio of the branching ratios. So here you can see the numbers. This is this ratio is the BS to S and divided by the BS to psi prime. But here there is something very interesting is the comparison with similar decays, let's say BD or B plus mesons, indicates that the X information, the S formation in the B meson, the case is different from the psi prime formation. This is suggesting that the S is not a pure CC bar harmonic stain. So, and in this way, this is supporting similar conclusions derived from other experiments. But this is very interesting because this is giving new light on the nature of this particle. So I just want to call your attention, and you have to review this paper. It is for sure very interesting. So now let's move to this other new result from CMS. This is the CPU annihilation phase. And here it's interesting because there are different things. One of them is, of course, we do a new measurement, and you can see here, this is very good. There is very good improvement regarding the previous measurement ATV. And besides, because there are new techniques that CMS is using here, and especially we are using improved opposite side tagging using machine learning techniques. And besides, CMS is using new trigger in this analysis. This trigger is a trigger that use 2 months for the SI and 1 month for the tagging. That give very nice improvement in the measurement. But let's say 2 comments. One of them is, so far CMS is using just partial quantity of the data set. It means just 2017 and 2018. That is very important because there is still room to continue with the other data, with the other part of the data set. And besides that, there are other comments here. Also, LHCb and Atlas present the results using, of course, the data set from there. And also they are using partial quantity of the data. So the 3 experiments can do new measurements using the full run to data set, but there are something interesting related to the delta gamma S. Here, the 3 experiments are doing different measurements. The tension in this measurement is not trivial, it's 4 sigmas. So probably it is not related to the statistics. Something is different in the 3 experiments. This is something with this is discussion in the 3 experiments at the moment. I am part of the discussion, and we need to understand what is happening. So again, I am taking your attention. Please stay tracking these interesting results because in the future we will do the 3 experiments will get new results in this point, and I think we will understand what is happening. So now let's move to the main of this talk. The main of this talk is as I told you, the BC2S and BC2S star cross-section measurement respect to the BC. And let's do very short introduction here. And here you can see, let's say this is the spectrum that we know of the BC particles. This is the BC, BC1S and BC1S star, and here BC2S and BC2S star. Here in the figure, you can see, let's say how is the transitions here. For example, the BC star can go to BC, and the reason is very low PT photon here. And here you can see the 2 states of 2S, BC2S and BC2S star. And the transition can be through the photons or through the 2 pions. Here are too many references which are related to these studies, but what I want to try to understand here is the following. If you check the BC2S star particle, it goes to BC star and 2 pions, where BC star goes to BC and this photon, where this photon is very low PT photon. So that is the reason why we cannot reconstruct that photon, because it's very low PT. We cannot do that. It's something like 15 meters. So the other channel is BC2S, and BC2S go to BC pi pi, and so what it means, we will see the two particles, BC2S star and BC2S, both then in BC pion pion. So in that point, we need to understand this expression here, because in this point, we will see the BC2S star, but we will see this resonance move to the left because the photon and the quantity is expected to be this one. It means is the difference or the mass difference of the 2s and 1s. So here, come on, sorry. Can you see my screen again?
Yes, we can see it.
Okay, sorry. I don't know what is happening, but something is not working fine here. Okay. So now, as I told you previously, here is the observation of the two-peak structure. Here is the BC, where the BC goes to GSI and pion. Here is the quantity of the yields of this channel, and here is the resolution. And here is the expression that I told you. As they use this base stage, we can claim the observation. CMS 1 year ago, CMS claimed the observation of this two-peak structure, where in this plot you can see BC2S and BC2S star, and as I told you, BC2S is in the left because this mass shift. So we can do the measurement of the BC2S mass, but we cannot claim the measurement of the BC2S star because this relation. But in any case, we can do the time measurement, and is in agreement with the predictions. So after that, LACB 2 months later or something like that, also do the analysis and claim the observation of the BC2S star, but the statistic is not enough to claim the observation of BC2S. In any case, they presented the mass measurement for the two peaks, which are in agreement with the mass measurement from CMS. So now, the important thing here is after let's say the discovery of the two particles, there are several results from theoreticians, and they suggest to make new measurements. Let's say the production ratio of the two states, the production ratio of the BC2S respect to the BC2S star, and also the try to study the pion mass invariant, because it is interesting to check if there is possible resonance there. So due to this, we want to do those studies. Just here is the definition of the efficiencies. You can see here is the reconstruction and the particles after the full chain. This is using Monte Carlo course, and the generate quantity of particles. Here we are using just the sample BC2S, but of course the definition are the same for BC2S star and for BC. And very important here is the fiducial regime that we are using is this one, is PT 15, and the rapid is 2.4. So here there is the results of the efficiency. In this part, the central part, this is the central value. Let me explain here. There are two systematic uncertainties here, and there are related to the finite size of the Monte Carlo sample, because we cannot generate infinite sample. And besides, as I told you, this is using full run 2, so there are samples for different years, 2016, 17, 18. That is the reason we need to consider one systematic, because the different years. And besides, as this is the BC2S regarding 2 BC, so in the case of the BC2S, for example, there are 2 pions, BC pi pi, so we need to consider the one uncertainty related to the 2 extra pions in those channels. So here you can see let's say the preliminary. These are preliminary results. You can see here the ratio measurements for the three cases. And also you can see here one comparison with Atlas and HCB. With Atlas, we cannot compare directly, because they didn't present deficiency in his results. That is the reason why we cannot do the comparison. We can compare with LHCb, even when there is no exact, the comparison is statistical, but we can try to do it. And what we found is the results from LHCb and CMS are in agreement, but clearly they are in disagreement with Atlas, or only they are in agreement in the case of the ratio of the efficiency of Atlas is very, very high. But this is probably not possible. But the message is this: we are in agreement with LCB, but we are in agreement with Atlas results. So other interesting here is to try to see there is any dependence with the PT or rapidity, because some papers suggest some kind of dependence in these Carconian studies. But as you can see here, we didn't see any trend. But unless at this accuracy level, we can see, let's say, there is no dependencies on the PT or rapidity for these studies. So here you can see the División mass spectrum. This is very interesting plot. You can see here in this plot there are just you can see here in the points are for data, and the histograms are for the Monte Carlo. As you can see here, I want to explain the Monte Carlo was generated as phase space. That is the reason. It means there is no resonance in the División in the Monte Carlo. So see, there is any particle what is mediated is the case, let's say B, C, rho and rho going to 2 pions, is not considering the Monte Carlo generation. That is the reason why you can see here probably some difference. But in any case, let's say something here. Even when we see some hints about the difference between Monte Carlo and data, the statistics is still not enough to say completely, yes, we can say there is resonance there. No, we cannot claim that at that moment, but we see some hints here, and we need to collect more data in order to get, let's say, a more strong statement here. So let's talk about the uncertainty and the systematic uncertainty evaluation here. And there are several sources or systematics. For example, the different sources are, for example, the modeling of the BC, the modeling of the BC2S, the Monte Carlo sample size, and there are different things. I will just want to explain a little bit about for example, in the BC modeling, we use, in the model, we use 2 Gaussians. But if we want to move the model, we can use, for example, 1 crystal ball function plus 1 Gaussian. And in the case of the background, we are using an exponential, 1 polynomial. So we can move to, for example, for 1 exponential function. And the change that we notice, we can assign these numbers as the systematic source. You know, when we move the model, we are moving the yields. And as you know, the cross section is related to the yields of the fits. And that is the reason why we consider this as systematic. In the case of the BC2S modeling, this is very particular because in the signal, we know this.
5 minutes, Giovanni.
Okay, thank you very much. In the case of the signal, we are using in the model, in the nominal model, we are using 1 Gaussian. But from some studies, we know from Monte Carlo, we know probably 2 Gaussian are necessary, but the statistics is not enough to fit 2 Gaussian. So the systematic is we move from 1 Gaussian to 2 Gaussians, but we fit the resolution from the Monte Carlo. And in the case of the background, we are using 1 polynomial, so we move to the threshold function and and consider this as the systematic. In addition, we generate too many toy Monte Carlo studies in order to understand if the feedback get good performance or not, if there are some variation, and then we found and we found this is good. And in any case, if some difference in the yield quotas and in the yields, we put the systematic uncertainty related to this. So other interesting thing is here, as I told you previously, we generate the Monte Carlo has phase space. That is the reason why there is no, let's say, the intermediate resonance there in the División system. So you can see here, after understand this, we made a reweighting on Monte Carlo. Let's say in red, this is the data. In green is the phase space model for Monte Carlo. So what we do is do a reweighting, and we move the Monte Carlo to be very similar as the data, as you can see here in the blue one is histogram. And after do that, we recalculate the efficiency with this reweighting Monte Carlo, and the difference in the efficiency is assigned as systematic. So finally, what we found is that here you can see the systematic studies for these channels. I mean, for these cross-section measurements, and you can see here the summary of all the systematic uncertainties related to the BC model, the BC pi model, efficiencies, as I told you in some previous slides, the DPO tracking, the kinematic, the licit angle, and so. This is here you can see finally the total systematic associated to these cross sections. And also there are some comments related to the systematics in the DPO mass distribution. With this is these systematics are related again to the models or the GSI pion or the BC pi. So finally here you can see the summary. We are using full run 2 data set to make the measurements of the cross-section ratios regarding the VC2S and VC2S particles. And here you can see also the ratio of the VC2S star to VC2S. And you can see here the numbers and the fiduciary region. And in this plot, you can see again the DPO mass distribution related to this site states of the VC. And we expect this cross-section relation and the DPO mass distribution is very important information in the nature and production mechanism of the CC bar or the CBB bar systems. Okay, thank you very much. So if you have a question, please go ahead.
Thank you, Giovanni. Any questions?
No questions on YouTube. And I don't see questions up to now.
You mentioned, Giovanni, that there was in the midnight we had no question that there was using just part of the data. There are plans to date this with the full data set?
Yes. In fact, right now, all the 3 experiments are working in use the full data set. Also, CMS is doing that. But in the case of CMS, we are trying to use not just the trigger that we are using at the moment, but there are other possibilities to join other trigger in the measurement, which will get some improvement in the statistics. Probably we will get the 10 times the statistics that we are using right now. But of course, we will lose some power in the tagging because this trigger is just GSI trigger, no GSI plus month trigger.
Any other questions? Well, if there is no more question, then we tend
no more questions. Also.
We tend Giovanni. Thank you very much, Giovanni. And
Okay,
this was the last presentation from this session. Any announcement, Salvador? Or something?
No, we have the winners of the poster. We have to review. We will let you know once we are back.
Okay, so in the next session, you will have this the announcement of the poster, which if you didn't have time to take a look yesterday, they are already still in the YouTube. So I invite you to go and take a look at them. That's, I think, was a very good job for the 10 presenters of the posters. So we now go to a coffee break, right? How long it will be? It will be back
20 minutes.
20 minutes, probably pretty much 11:05. All the presenter of the morning, and see you in 20 minutes, more or less.
So we are about to restart. Can you hear me?
Yes.
Salvador.
Thank you. Before, Karen, before you start, I would like to give an announcement about the poster sessions. So we will announce the winners. We would like to thank the work of the jury for Alexis Aguilar from UNAM, Pedro Podesta from UAS, Mario Ivano from UAP, and Alfredo Castañeda from Unison. So the winners of the poster, we have very tight competition. We have Osvaldo Miguel Colín, presented CMS RPC longevity. Can you hear me now? And Andrés Ramírez Morales, Frontiers in Particle Physics through Precision Experiments and Machine Learning. So we will give them later the diploma. Thank you. If you want to proceed, Karen.
Hola, buenos días.
Buenos días.
Good morning, sorry.
Oh, yes. I will stop sharing.
Okay. I was not aware of this, but we can continue anyway.
Okay. I can send you the program. So now it's Jose Feliciano.
Okay, you want me to start?
Yes, please.
Okay, thanks. Yeah, so good morning, everyone. Let me start sharing my presentation. Are you able to see my my slides?
Yes, we can see them.
Okay, good. So right, so my talk is very general on some on the CMS experiment. I'll be showing some overview of the activities in this experiment and a small sample of the recent results in the different areas of research for this experiment. This is a brief, it's an outline, so just a brief introduction, the status of the LHC, the luminosity we've integrated up to this point, about a little bit about how the CMS publications are distributed, and then I'll show some results in these areas that I list here. They're not all the areas in CMS, but it was there's way too many results to really cover in 40 minutes. So I'll just cover a few in these areas. I also then want to comment a bit on the future of the experiment, what is going on in terms of upgrades and plans for towards the run 3 in high luminosity LHC. So where we are now, this is a timeline for the LHC and high LHC experiment. We are still in this period of long shutdown that started last year, after accumulating 3 years of 4 years of luminosity in run 2, there was already a long, let's say, end of the year technical stop here where some improvements were done to the experiment. But now a lot of upgrades are being done both on the LHC and in the different detectors. So there is some delay on that's going to happen next year, where we were supposed to already ramp up in run 3 due to the COVID lockdown. In fact, we are not expecting physics runs in 2021. But nevertheless, the LHC will restart, and some collisions will happen. Then, of course, later on, we will come back to the upgrades for the high luminosity LHC, where a lot will be done to the LHC and as well to the experiments. I'll talk about that at the end. Okay, so so far we have with the 2018 data set, we have more than about 150 inverse femtobarns of data. That's about 15 times the data that was used for the discovery of the Higgs boson. So we're quite a bit up now. And so what has been seen is that the LHC has been performing outstandingly. Now in 2018, it already was running at 2 times the original design value for the luminosity, which was about 1 times 10 to the 34. We were running at about 2 at the end of 2018. And that translates into a large amount of pileup. Unfortunately, we had to deal with that. In 2018, we had an average of about 37 collisions per bunch crossing. And in 2017, even slightly more due to some special running here. So anyway, so this is the price we have to pay for luminosity. We have to deal with more noise in the detector, let's say. In terms of papers, we reached a very important, significant milestone in CMS with submission of the 1000 paper just recently at the end of June. And here you can see how those papers are distributed in the different areas. So you can see the Exotica group is leading here with they have a lot of models they test and ideas for searches. And then you can see how the standard model measurements are there. And then supersymmetry Higgs and so on top are the ones that are contributing a lot. Okay, so what, to give an overview, and this is a very busy plot of what measurements are done, and this is just for the standard model. The range, as you can see here, for these processes, which are the single bosons, W and Z, multi-boson processes, top and Higgs, there is a very large variation in the production cross sections, which spans about 10 orders of magnitude. And nevertheless, we have with the data set that has been collected, due to the large amount of luminosity, we've been able to measure this even very, very small processes like QQZ. Okay, so now going into just a sample of results in the detector performance or object reconstruction needed for those searches. I wanted to just show this paper or this result on the pileup jet identification. As I mentioned before, we have to deal with a lot of pileup. And so this is a very important result for which affects many measurements. And you can see here a diagram of what can happen. Of course, there is the interesting collision, which we call the hard scatter, and usually is identified by looking at the tracks which are associated with it and assigning or identifying it by the one which has the largest sum of the PT of the tracks. And then the other ones are then assigned as pilot jets. And there can be two types, one which are real jets and other jets which are just fake stochastic or random energy deposits in the detector. So it's very important to remove this from the reconstruction of our signal events. And you can see here that this paper or these results with the new trainings in 2019 are really doing a very good job in removing the pilot jets. So this plot shows the number of total jets and the pilot jets as a function of pilot. And of course, we want to keep this at constant, meaning we only keep the hard scatter jets. So after applying a cut on this algorithm for pileup identification, you can see how this pileup is really mitigated, and we have almost a flat reconstruction of the jets. There was a huge improvement in the training in the forward region due to an improved pixel detector, which was installed in the technical stop between 2016 and 2017. And you can see that here in the trainings in the efficiency curves versus missed tag rates. That is because this tracker was upgraded and with better end cap performance. I'll come back to the tracker later. Okay, so then another interesting result in the object reconstruction are what we call large R jet tagging, which aims to reconstruct boosted objects, which can be, for example, W's, Z's, or tops. And the reason for that is then you have more tools to search for new physics or to measure the standard model processes in more in different phase spaces. So what happens here is that as the Z's or the W's or tops become very boosted, their decay products, which can be quarks, will then merge into a single jet, which normally would not pass the small radius jet reconstruction. But if you then enlarge this radius of reconstruction of a jet, then you can recover those jets. Of course, then you have to identify what they are. And that is done by looking inside the jet and identifying if it has like a two deposits here. We call that the ends of jettiness, and is this tau 1, 2, tau 3, 2 variables, which are then which are like the probability of having 2 versus 1 inside or 3. And then you can see those distributions here in this TT bar sample, how at low values here, we have a large contribution of merged W's. Okay, so those are the boosted. Okay, the agreement here between data and Monte Carlo is not perfect, so one has to then measure what we call scale factors for the reconstruction, and that's done by fitting the mass of the jet, which in this case peaks at the W mass, and then extracting here the amount of signal and comparing that to Monte Carlo, we understand this deviations from the Monte Carlo from the simulation, and a similar thing is done for the top. So again, here, now using the tau 3-2 variable, one is able to identify boosted jets, which correspond to the top. And here you can see clearly this mass peaking around the top mass and a similar procedure. So this paper addresses this reconstructions. Okay, going into some results in the electroweak sector. And following from from the boosted object reconstruction, we have this new result, which is the Higgs in the boosted topology. And this aims at understanding the Higgs production at large momentum. And you can see here the theory curves for the different processes that produce the Higgs, which are gluon fusion, BBF, vector boson fusion, associated production with the Z and W and TTH. And you can see at very large momentum, these processes are similar. So this measurement is important for understanding what's going on here and if there's any deviations. Of course, it's very difficult because there will be a large amount of background, which you can see here in the plots. And this is the mass of that boosted jet in different momentum regions, 500 to 600 and so on, up to 1200 GeV. And here the pink is supposed to be the Higgs contribution. Of course, here we're talking about a Higgs to BB search. Okay, the result after the final fit is that we have a slight excess of events, which corresponds to about 2.5 sigma. So not yet an evidence for the Higgs in this reconstruction, but consistent with the standard model. Okay, so going from that very specific search to the grand combination, let's say, for the Higgs, there is, okay, I have links, but I'll have to load the presentation where you can find this results, and this is the latest combination of the Higgs measurements. And there's now a nice table showing the different searches in terms of production mode and in terms of decay mode. Are you able to see my mouse actually? I'm not sure.
Yes, yes.
Okay, thanks. So then, for example, the gluon fusion is dominated and was the discovery channel by the diphoton and ZZ decays. If we go to the vector boson fusion, this is a diagram. This is dominated by tau tau and gamma gamma. Then there's the associated production with a W and a Z. Here, the BB bar decay channel is the one that dominates. And then you have the TTH production, which again, BB bar contributes in the largest. But then there's many ways to reconstruct it. In fact, this is the channel which has all these different ways. And then using all these channels, what is done is a global fit using the coupling modifiers, so the so-called kappas, which are the deviations or the ratios to the standard model parameters for each of the couplings. And now we're talking about the actual couplings to different particles, including some effective couplings here, like the photon and the gluon. And you can see, okay, so the data sets that are used here are not the total ones from run 2. In fact, only the ZZ channel is using the full data set, which is about 140 inverse femtobarns. In the other channels, like gamma gamma, tau tau B bar, WW, we only use up to 2017, and mu mu, I think it's only using 2016 data. So with those data sets, then you perform this global fit. Of course, a more precise one will come later, but you can see what kind of uncertainties we're getting already for this combination, which is on the order of 7% total uncertainty on the Z coupling, order of 14%, or maybe 11 and on average 10 for the W, and so on. Okay. All these are as you can see from the diagram, are consistent with the standard model. If you want to talk about small deviations where the WH is slightly up, but the BBF is slightly down, below 1 sigma. Okay, so these uncertainties will of course improve, and the goal, of course, of the high luminosity LHC is that we will reach order of 3 or 4% in these final uncertainties, which will be a very stringent test to the standard model and new physics. All right, moving on to other processes. This is a very, in this case, a rare production of tribosons, which tests the quartic gauge couplings of the standard model. So of course, you need this kind of couplings in order to produce 3 bosons in the final state. And this new result claims a first observation in the combination, okay? So for individual channels, we have only evidence, slightly above 3 sigma. When you combine that, that goes up to higher than 5 sigma. So the combination we claim, the first time we observed this triboson production. Down here, you can see the distribution of events and how that is distributed along the different reconstruction channels. All of these channels are leptonic, and due to the large number of bosons, you can have between 2 and 6 leptons in the final state. Okay, going to precision measurements. Here's a result on the differential cross section for the Z or the Drellian, Z and gamma. And here it's also going to high PT, so it's interesting to understand if the Monte Carlos that we're using are modeling properly the Z and the photon momentum distributions. So this is, you can see here, of course, the reconstruction here is in the cleanest channel, which is the Z to mu. And here, for example, you can see the extracted cross-section as a function of PT of the Z. And there's quite a good agreement with these MATGRAPH Monte Carlo, which is the most precise generator that we're using. There's only one bin here, which looks quite a bit off, but it looks like a data. Maybe it's something with the data here, fluctuated downwards. And then for the photon, you can see even more precision here. So it's very, very good agreement with this Monte Carlo predictions of the spectrum of these processes. All right, going into some results in the top physics. Different again. Now going to precision in this channel, which is the TW channel or TW production. This can be generated through these diagrams here, where you have a gluon from one proton and a B, which usually comes from splitting of another gluon in the other proton, and then you produce a top and a W. Now you can have some interference with the TT-bar process, because that also produces the same final state. So it's important to measure the differential cross sections to understand and disentangle any effects. The reconstruction here is done again in the leptonic channels, the top leptonic channels, with one muon, 1 electron, and 1 B-jet in the final state. And here you can see the event distributions as a function of 3 different variables. One is the leading jet PT, leading lepton PT, leading jet, and the delta phi between the electron and the muon. And here the extracted cross sections as a function of those variables. So for this process, okay, here we have the Pauheg generator comparison, and the agreement is within the error bars, let's say, except for the low PT. Okay, in both distributions, you can see some slight disagreement And if you look at the ratios, so there's some trend here, okay? It's not too surprising for this kind of processes, which are very difficult to model, but it shows that it shows the importance of measuring this kind of events. All right, then you can see here another sort of precision type measurement going in, trying to measure the kinematic distributions. And in this case, it's an interesting way to try to measure the Higgs coupling to the top. And how this is done is that with the large amount of data, we can try to look for interference between the leading order and the next order diagrams, where Higgs can be exchanged, or even other particles between the top. And so this kind of interference will have effects on the kinematic distributions. For example, the top, the TT bar mass system, and the rapidity difference. So looking for this kind of effects, which arise if you would have a different Yukawa coupling, we can measure the coupling. And here's the, using the full data set here, 137 inverse centibarns. Now it's difficult to understand how the events are plotted here, but there's a different years, 2016, 2017, 2018. And then these are split by the rapidity region in 2 regions. And then within each region is the mass distribution. So you make a global fit to this total data sets. And the nice thing is that the data set is very clean. So all the red here is TT bar. And you can vary the shapes and extract a likelihood scan for the Yukawa coupling. And this is consistent with the standard model, as you can see here. Okay, now to mention a couple of results in the SUSY sector. This is like a classical search for SUSY. So you search for pair production of top squarks, where these will indicate to a top and the neutralino or LSP. And there's a couple of different models that can be tested. Another one where it's not, where the W and B are produced through this chargino. Of course, in both of these final states, you have a very large amount of missing energy due to the this neutralino, and so you search for missing energy in the event, among other variables used in the reconstruction. But here you would see, for example, here you can see the distribution of the signal or potential signal here, and if you had more, then this would lift the tail, and we would be able to observe it. This data is also corresponding to the full data set, and there's no axis. So we place limits on the cross section for this kind of a signal as a function of the masses of the super particles here in these 2 different models. In the Exotica group, one of the interesting results is the search for long-lived particles. And this requires non-common reconstruction, let's say, of the event, because even at the trigger, you have to make sure you keep this event. So there's a special jet trigger where these jets are allowed to be displaced from the interaction region. And you also require a large amount of PT, some PT of jets in the event. And in the offline analysis, what you do is you make all combinations of dijets, so 2 jet combinations. And then you look for a displaced vertex from the interaction region. And of course, the tracker in CMS is very good at doing that because they have very, very good precision, order of less than millimeters, to look for displaced vertices. So down here, you can see, for example, the significance of this distance in the transfer direction of these vertices, which are reconstructed. And here, the multiplicity of those vertices, the track multiplicity. So if there was a signal, then you would see it would look different like this in the multiplicity, and sort of like this in the tails of the distance. Okay, so you can see there's no excess in the data. In fact, maybe it's modeled in here. And then limits are placed depending on the lifetime of these particles. And they will depend obviously on the mass of these potential particles. Okay, so here you can see those limits. Okay, so now moving on to back to the detector, the experiment. We are approaching the high luminosity LHC. So a few years is really not that much to upgrade to make the necessary upgrades for the detector, which are actually many, because the conditions of running will change very significantly, factor of 4 to 5 in the instantaneous luminosity across this long shutdown. So in fact, just to give you a short history of the high luminosity LHC, so it was initially placed at the highest priority in 2013 after the discovery, and then formally approved in 2016. Then in 2015, we had the technical proposal for the CMS upgrade, which gave an overview of what needed to be done. And then from that, you can see how many or most of the systems have already produced their technical design reports for this upgrade towards the high velocity LHC. Okay, so in this include the tracker, the barrel calorimeters, the muon detectors, the DAC, which will change very significantly to deal with the high rates. And the end cap calorimeter will be transformed quite a bit. The trigger, of course, there's all these developments, and so there are more to come. So in Mexico, we are involved in some of these developments. So I want to make sure to cover some of these. Of course, it will be a very intense running period with very large amount of radiation accumulated in the detector. So that's a very important aspect to consider. With regards to the tracker, you can see here, in fact, the tracker was already replaced one time, the pixel tracker. This is already the phase 1 upgrade, which is currently running. But then you can see how this is going to evolve very significantly towards the high luminosity LHC. So the entire forward region will look quite different. And this is important because with the much larger pileup, order of 200 vertices, then we don't want to have a problem, or we want to be able to reconstruct those vertices as best as we can. And of course, a lot of those events go in the forward region because those are minimum bias. And so this is an important part to be able to identify all of the pileup. The other thing you can see here is in the outer tracker. This is what's called the outer tracker. And the sensors will be slightly placed in a smarter way to make sure that the tracks are properly better reconstructed with capturing more hits. Okay, so those are the main changes. Also, another thing that was not currently present is that the auto tracker will send the data also to the level 1 trigger. So we have a level 1 tracking in the reconstruction, which will help to identify the, for example, isolation. Now going into the calorimeter upgrades. So for example, here in the end cap, because of the radiation it suffers, in fact, the current calorimeter is performance is very much degraded already, and in run 3 will be very much the efficiency will be very much down. It's because it's using this crystals in the ecal part, which lose their transparency. Also the scintillators in the HCal. So there will be a very large change in the forward calorimeter for phase 2, which is to replace the entire region with a silicon-based sampling calorimeter. So this has now this sort of silicon wafers, hexagonal in layers with absorbers in between. And there's the ecal part and then the HCal part, which will use both silicon in the region where the radiation is the strongest, and then in the lower radiation part, it still uses the scintillators. Okay, so that this is currently under development. It's one of the major changes in CMS. The muon system will also be improved, and notice how there's a focus on the forward region. Okay, in the barrel and the this part of the end cap. So we will keep more or less the same detectors. There's different systems. There's different kinds of sensors or chambers used, called the drift tubes. In the barrel, the cathode strip chambers in the end cap, and then there's RPCs everywhere. So in the forward region, there are some new detectors that will be installed. It's called the improved RPCs and the GEM detectors, as well as this ME0 here, which will allow, which are able to cope with very high rates of particles and will allow good reconstruction of muons in this region. This goes with the improvement in the acceptance of the tracker as well. Okay, as I mentioned, as I showed before. Okay, I think this is the last. Now there's a very nice new detector which is going to be installed, and this is called the timing detector, the MIP timing. This is the best diagram I could find. So the idea here is that you can, that there will be a layer, thin layer of sensors installed in the barrel and in the end cap with a very, very precise timing resolution for the tracks. The technology that will be used are this so-called lysocrystals in the barrel, and then in the end cap, this silicon-based LGAT sensors. Yeah, silicon we need for the higher radiation. Now with beam tests done on this kind of sensors have shown extremely nice timing resolutions, order of 20 picoseconds, 20 to 30 in this LGATs, as well as radiation hardness. So why we want to install this? Well, it will improve the search capabilities for signatures where you have, for example, this, as I mentioned already before, this long-lived particles. But not only for the new physics searches, but also for the standard measurements. Because if you have 200 pileup collisions, those will produce a lot more noise than what we have now. But not only that, they will also destroy the resolution, the energy resolution on the particles. So if we are able to identify all those vertices, and here we're talking about identification not only in position, so the vertices, not only in position, which is shown here in the x-axis, but also in time, right? So if we have now a very precise time, we can probe the time distribution of the bunch crossing. And the bunch crossing, of course, is only order of plus or minus 300 picoseconds. So you need this kind of resolution to probe when the collision happened, in addition to where it happened. And so these allows to disentangle the pileup from the hard scatter vertices. And so, okay, you can see here. Otherwise, we would have a very large degradation in the energy resolution of jets, for example. All right, so this is in the works. TDR is still being developed. And that was my last about the physics. I just wanted to mention here that Mexico is very actively participating in this experiment, so in many areas. So for example, in the flavor physics, you already saw some results by Giovanni, Higgs top, BSM, and heavy ions as well. The RPCs, a very strong contribution there from Simbesta, Vivero, and WAP in operations and towards upgrade. In the luminosity system and radiation simulations, recently, as Unison joined CMS, we started this participation, and we've had some success there, and also some collaboration with the other institutions. There's also some contributions in the computing from Simbesta and Bob. So yeah, so we're very actively in CMS. Okay, so I come to my summary slide. So the LHC continues to produce a very rich spectrum of interesting physics. Okay, so far no deviations from the standard model, but the precision measurements that some of which I showed you are very much improving our understanding of the parameters of the standard model. Of course, we're coming into the run 3 in about a year, which will about double the data set. And then a lot of work is being done towards the high luminosity upgrade. And again, just wanted to mention our participation there. So thanks a lot.
So thank you very much for this very nice and interesting talk, Jose. So do we have any question?
Let me check. Can you hear me? Yes, let me check on the YouTube. There is no, we have 20 people following, and I don't know, somebody wants to, nobody has raised their hand up to now.
I have a question. It's a very technical one. So on slide 24, it is mentioned that there is this experiment for the long-lived particles based on CPM.
Sorry, which slide?
24. Ah, no, sorry. Well, I have another question on this slide as well. So these scintillators are crystals, so they are not plastic.
Oh, these ones?
Mm-hmm.
Okay.
So the question is if these kind of scintillators based on crystals are expensive in comparison with the ones of plastic, or what is the advantage of using this kind of?
Oh wait, these are crystals which are currently used. Yeah, yeah. No, the problem is not that they're expensive. The problem is that they lose their transparency, and so you lose a lot of signal with the radiation. So they're not basically they're not radiation hard for the high luminosity LHC.
Okay. So that's why it is going to be improved.
Yeah, that's why we need to go to silicon, because that's the only material that can withstand the radiation in this region. It's a very, very strong radiation region.
Mm-hmm. So the other question is on the CPM.
Sorry, which one?
The CPM, the silicon photomultipliers. So this kind of detector, I know that are very sensitive to high energy radiation. So have you tested some effects on aging on these detectors, or
On this wafer?
No, the CPMs. I think it's 2 slides later.
Here.
There.
Okay.
Yes.
Oh yeah. So right. So the thing is that these are not going to be placed in the in the highest radiation regions. So this is going to go in the barrel. So here.
Yes. Okay. Far away from the.
Yeah. There's
the lonely particles. Okay.
Yeah. Well, I mean, this region, the barrel region is not going to see so much radiation as the forward region. Okay. So yeah, the radiation tests have been done for the components of these detectors. Yeah.
Okay, thank you.
Mm-hmm.
Are there more questions?
No, no more questions.
Okay, so we thank you again, Jose, for this nice talk. And we go now to Christophe Royon from the University of Kansas.
Hello? Can you hear me?
Yes, we can hear you.
Very good, thank you. So let me try to share and let me know if it's working. Can you see the slides?
Yes.
Very good. So what I will discuss today is some studies about anomalous coupling. So I will define what I mean by this using the forward proton at the LHC. So I will first of all discuss the proton tagging at the LHC. Also, I will mention different anomalous coupling studies. So I mentioned 4-photon anomalous coupling, or 3-photon and 1 Z boson, 2-photon, 2 Ws, 2 photons, and 2 Z boson. Also, the possible observation of W pair exclusive production, and at the end, also the search for axion-like particles. So on the second slide, so basically I want to define how we can detect intact proton in the final state. So in CMS, we have a new apparatus that is called the CMS Totem Precision Proton Spectrometer. So there is a schematic which is here. So you have only on one side of CMS, but it's on both sides of CMS. And we integrated basically some forward proton detectors that are coming from Totem into the system, the CMS system. Sorry for that, the kind of alert, I don't know what it is. Okay, good. So basically what we are doing in order to detect the intact protons is that we are using the LHC magnets which bend the scattered protons out of the beam envelope. Since the protons lost part of their energy, they can be detected inside this Raman post detector. So the idea is to detect the scattered protons a few millimeters from the beam, again on both sides of CMS. And we collected already about 100 inverse femtobarn, even a bit more than 100 inverse femtobarn of data using both CMS and this forward proton detector. Atlas has similar detectors, which are called Atlas Forward Proton, or AFP. So just to give you some feeling, first of all, before we go into the detail of which kind of physics that we can do. So there are two diagrams. The left one is basically you have proton-proton interaction and you produce two jets. So this is basically, you see that this is a QCD interaction, two protons are intact and you produce two jets and nothing else. That's why we are calling it exclusive events. You have two protons plus two jets and no energy loss in other particles that are produced. Or you can have also gamma-gamma interactions to produce a system X, as it is shown on the right diagram. So the idea is also to give you what is the kind of acceptance that we have. So it depends how close you can go to the beam. But you see that this is the mass distribution of this event. And you see we start the acceptance around 500 GeV up to above 2 TeV. And when I'm saying about mass, this is mass of the two jets, which is here, or the mass of the system X in the case of photon-photon interaction. So what we are using in Monte Carlo that we built, I mean, we have been building for many years, which is called Forward Physics Monte Carlo, which used to produce all diffractive and photon processed events. And also I should mention that we have a complementarity between low and high mass diffraction, because in fact there are special runs at low luminosity without pileup where we can do low mass diffraction. And what I will concentrate on this talk is only high mass event. I showed you this acceptance, which is in normal running at the LHC, where we can do also exploratory physics. So in slide 3, I just want to start by discussing this kind of typical anomalous coupling that we are going to study. So there are two diagrams as an example that we want to study. So these are photon-photon interactions. So you have quasi-real photons that are emitted by the protons. You can produce 2W events as an example, W plus, W minus. And again, it's exclusive because you have two protons and 2W and nothing else. And again, we'll see in the following that this is quite important. Or something else, another example, is to produce two photons in a final state and also the two intact protons. So just to give you some feeling, in the case of WW, the standard model cross-section is of the order of 96 femtobarn. And if you ask the mass of the W pair to be above 1 TeV, you still get something like 6 femtobarn. So it means if you are talking about 300 inverse femtobarn of luminosity, like it's usual at the LHC, you are getting plenty of this kind of events. So on the next slide, I will first discuss the standard model contribution before going to the anomalous coupling and beyond standard model. So I will take the example of two photons produced in the final state, and as usual, of course, the two protons. So there are two diagrams in two ways from the standard model point of view to produce two photons and two protons. The left one corresponds to QCD interactions. You see that there are some gluons that are emitted. You have a loop of particles and two photons are produced. Then the right diagram, you have a gamma-gamma interaction. Again, a loop of a charged particle. So this can be quarks, leptons, or W boson. And they produce these two photons in the final state. What is shown in the bottom plot is the integrated cross-section in femtobarn as a function of the cut on the diphoton mass. So the diphoton mass is the two photons in the final state. The upper diagram, which is the pink one, corresponds to the QCD diagram. And you see that it's going down very fast as a function of the diphoton mass. The value which is here is about 200 GeV, and you see that at 200 GeV, it's already very small. Where the contribution for this diagram, the right one, which is a photon-induced process, corresponds to the black line, which is here. So it's clear that you are in the mass acceptance of our detector. Let me go back one slide. So I showed you that the acceptance starts something like at 500, 400 GeV. So it's basically clear that we can ignore the left diagram, the QCD diagram, with respect to the photon-induced processes. So it means that if we detect two photons and two protons in the final state, this means that it's a photon-induced process at the LHC. So what is the motivation now to look for this kind of events? So there are, this is basically the two kinds of coupling that are possible. You can, as we said, you can modify the diphoton production by loops of new particles, or via a resonance, which is the right diagram. So this is the Lagrangian, which is shown here on the formula. So the left diagram corresponds to new couplings, which is called zeta1, which is proportional to the force power of the charge of the particle divided by the force power of the mass, and also proportional to the spin of that particle. And it leads to basically coupling, which are predicted for typical beyond standard model events of the order of 10 to minus 14, 10 to minus 13, GeV minus 4. So if you go now to the resonance part, the second diagram, you can also compute the coupling, which is shown here in blue. So this is proportional to the coupling gamma-gamma to Higgs, so gamma-gamma to the resonance to the power minus 2, the mass of the resonance to the power minus 2, and also the spin of the particle. And again, if we assume like 2 TeV dilatons, for instance, for beyond standard model physics, we expect this kind of coupling to the order of 10 to minus 13. So we are now going to see if we can be sensitive to this kind of couplings at the LHC or not. So let me do one aside on the way, which is to remind people what is pileup at the LHC. So what we have at the LHC is the proton-proton interaction, as is shown here. For our events, both protons are intact, and we produce, for instance, two photons that can be detected in CMS. But at the LHC, we don't collide only one proton with one proton. We collide many protons with many protons, or what we call bunches of protons that collide together. So it means that there are many interactions between two protons that occurs within the same bunch crossing. So they are represented here by these different stars. So you see that these events in the bottom that we would like to reject, where you produce two photons from these interactions, but in addition, you have additional protons, which are coming from additional pp interactions from other stars, as you can see. And this we want, of course, to reject. This is what we call pileup at the LHC. So here I represented only 6 events of pileup, but you imagine that at high luminosity, we get up to 50 such kind of interaction at the LHC. So this is clearly a high background that we need to fight. So on the next slide, let me show you what we expect, for the number of events. So this is again, gamma gamma going to 2 photons plus 2 protons intact in the final state. And what is plotted here is what is the cross-section for the different processes. In black, you have the anomalous coupling for 2 different values, what we predict for the number of events for 300 inverse femtobarn as a function of the diphoton mass, for 10 to minus 13 and 10 to minus 12 GeV minus 4 on the coupling. You see that basically this is the standard model background, which is like a gamma gamma going exclusive production. So the standard model exclusive diphoton production is basically negligible. And the only background which remains is the one which is in red, the world curve which is here, that corresponds to diphoton production plus protons originating from pileup events. So I just put this kind as a reference, if people want to get more details. So how are we going to fight this kind of events? So let me go back to 2 slides about this, or 1 slide. So this is this kind of events in which we are interested in. So you see that for our events, we have 2 photons that are produced, 2 protons, and nothing else. So this means by energy or momentum conservation, if we measure for instance, the mass of the 2 photon system and the mass of the 2 proton system, they should be the same. And it's also the same for the rapidity distribution. The rapidity of the 2 photon system and the rapidity of the 2 proton system must be the same for our signal events. Whereas for pileup, as I told you, for pileup, my 2 protons have nothing to do with my 2 photons. So of course, it should not be the same by definition. And this is what's illustrated on this plot, where you have the ratio of the mass of the 2 proton system divided by the 2 photon system. The signal is in black and the pileup is in red. You see that we get an almost flat distribution for pileup, whereas the signal is peaked around 1 according to the resolution of the detector. And the same for the difference in rapidity between the 2 photons and the 2 protons, which peaks around 0 for the signal and which is flat for the pileup events. So basically, I will not enter into the details, but what I want to say, so basically we get no background after cuts for 300 inverse femtobarn, and we get a sensitivity which is up to a few 10 to minus 15 at the LHC. And better by 2 orders of magnitude with respect to more standard method at the LHC. So we reach this, what is predicted from by the beyond standard model events that we discussed before. So on slide 10, I want to mention also another application, so which is related for action-like particles and can be produced in the same way. So this is the same diagram as before, where you see gamma gamma. They can produce an action-like particle that decays into 2 photons. So in the same way that we will be sensitive to the anomalous coupling, or in other words, the anomalous coupling result can be reinterpreted on some sensitivity to action-like particle. And what is shown on the plot is the coupling versus mass of this action, and the sensitivity at the LHC is in the gray area. So this is what would be the reach that would be possible to do by detecting the 2 photons in CMS and the 2 protons inside the totem detector. So you see again that we cover a domain that cannot be covered at the LHC without detecting the 2 protons. I should mention also, very briefly as at the parenthesis, like there is also the possibility to use heavy ion runs to study also this. So what I wanted to show you is because for the heavy ion runs at the LHC, you can be sensitive to lower mass of the action-like particles. So there is, of course, low luminosity in heavy ion runs, but since the cross-section is proportional to Z to the 4, Z of the heavy ion, the cross-section is increased by a lot. That's why we can cover this lower mass domain around 10 GeV, you can see or below, if we have lead-lead collisions, proton-lead, or argon-argon collision. So this is complementary to the coverage that we had in proton-proton interaction. And we get the similar gain of 3 orders of magnitude, as I will show you in the next slide, also for 3 photon and 1 Z coupling. So this is basically illustrated on this plot, the same basic idea. So you have still the 2 photons that are emitted by the protons. The protons are intact in the final state. And instead of producing 2 photons, as we studied until now, we produce 1 photon plus 1 Z boson. So we are definitely sensitive to gamma, 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 Z anomalous coupling. And what we studied is the decay of the Z boson, both from the leptonically point of view and also into hadrons, which is also not easy to do if we don't detect the proton in the final state. So this gives you, again, the number of events of signal that are expected in black as a function of the gamma Z mass, and the background, which is here in red, which corresponds again to the pileup background, the same as before. So the same trick, what we do is to measure the ratio of the gamma Z events divided by the 2 proton events, and the same difference in rapidity between the Z gamma center of mass measurements and the 2 proton events. So you see that for the signal, of course, we get a wider distribution because we consider the case where the Z boson decays in jets. So of course, the jet resolution is much worse than the lepton or the photon resolution. That's why it's wider. But still, I mean, cutting on these variables allow us to get a negligible background, again, for 300 inverse femtobarn and 50 pileup. And compared to the usual method at the LHC, we get
5 minutes.
Okay, yes, thank you. So we get a best expected reach, which improved by 3 orders of magnitude. The way that usually people look for this kind of anomalous coupling at the LHC is by looking at the Z boson decay into 3 photons, which is very difficult to look at, especially at high luminosity. So I want just to discuss, I mean, a few items which is related to the standard model observation now for WW events. So WW events, they can be produced by photon interaction, by the diagram, the 3 diagrams which are here. And the idea is to observe also the standard model case for WW production. And we will do it at high mass because we want to detect the 2 protons in the final state. And we study all the decay channels for the W boson. It means each of the W decays in a fat jet, so we have 2 fat jets, or one decays into lepton and neutrino, and the other one into a fat jet, or each of them decay in lepton plus neutrino. So what we expect for the standard model prediction is about 120 events for 300 inverse femtobarn after the different requirements that are indicated here. And we studied all the possible background, which are mainly due to WW, WZ, ZZ, W plus jet, Z plus jet, TT bar, and dijet standard model productions, plus again, the pileup, as usual. So the background is obviously quite high, but it can be reduced to about 20% of the signal, even using, again, these matching techniques that allows to reduce strongly the background. So this would lead to the first possible observation of exclusive WW at high mass with the data that have been accumulated and also the data that will be taken after the shutdown. I was just to show you that also it's possible to study it the same way gamma-gamma to WW events, the anomalous coupling, and the same method as before. So what is shown on this plot is the mass of WW events. You see the standard model in red and the effect of anomalous coupling here in the dashed curve. So this beyond standard model events, when there is anomalous coupling, they appear at much higher mass of the WW events. So we can separate the standard model contribution from basically an hypothesis, hypothetical, the standard, beyond standard model due to anomalous coupling contribution. And the sensitivity will be down to 3 × 10⁻⁷ GeV-2. And I'll just remind you that the present limits, which were done at low pileup using exclusive production of WW without detecting the proton, is more of the order 10⁻⁴. So again, we gain almost 3 orders of magnitude by detecting the proton in the final state. I just want to mention, on the last slide, I mean, we are starting also to study in the same way TT bar, anomalous production, or standard model events, so just starting. The standard model cross-section is quite low. It's about 1 femtobarn. A few events might be observed with 300 inverse femtobarn, but really probably to analyze this kind of events and measure it precisely, we will need the high luminosity LHC or 3000 inverse femtobarn. So I just want to, before the conclusion, to mention that in 2019, so last year, we had a very nice workshop on forward physics. So this includes partly this thing that the EIC, the LHC, and cosmic rays. So this was in Guanajuato, and David was hosted us in Guanajuato. So we were quite a nice group of people. We had a workshop there, so it was very nice. And the proceedings will be basically published soon by the University of Kansas. So we'll be able to read the proceedings of this workshop. And Christian and myself, Christian Badenegro, were basically, together with Martin and David, we were responsible for dealing with all the proceedings and the main part of this organization. So let me come to the conclusion. So basically what I showed you is the LHC to be seen as a gamma-gamma collider. So this allowed to look at all this kind of possible anomalous coupling because we study exclusive process, which is a photon-induced process. The theoretical calculation is of course in good control because it's a QED process. What is important is that it's a background-free experiment by tagging the proton in the final state, which leads to the best sensitivity possible on this coupling and also to axion-like particles or composite Higgs kind of model in much better way than it is done now at the LHC. So that's why, I mean, we are pursuing this analysis, and I should say that the first preliminary result on 4 photons should come out, for instance, for iCheck, so fully stay tuned, and we'll get some more results. And I just want to show you one last slide. I mean, to see basically what I propose is some new method to look for this beyond standard model physics. So we scheduled all the methods that are available to us to look for beyond standard model. If not, we'll be like these people. I mean, they are definitely missing the lion, which is just on their back. So thank you very much.
So thank you very much to Christoph for this talk. And we have one question from Pablo.
Yeah, so can you measure W's polarization? I'm thinking of the interest of longitudinal polarizations.
Yes, so I mean, of course, it's not easy, but probably by measuring the value of T, we can be sensitive to this. I mean, this has to be studied theoretically, but maybe there is a possibility to do it, but it has to be studied with which precision. I mean, I cannot tell you with which precision we could do it, but it's a nice idea. I agree.
Very interesting, thank you.
Yeah.
There is another question by Wolf.
Yes, thank you. I was wondering, for instance, this coupling 3 gamma Z, how do you incorporate this in the Lagrangian in a gauge invariant manner?
So the way, for instance, when I put the formula, let me go back a couple of slides. When I discussed the gamma-gamma. So what we did, yeah, here it is. So what we did is incorporating this inside the Monte Carlo. So what we have in our FPMC Monte Carlo is the standard model. And this, of course, depending on the parameter, we implemented the matrix element inside the Monte Carlo. So this is the way we do it. And the way that it's working in FPMC, if somebody comes with a new model, I mean, like for instance, I don't know, for Higgs or a new Higgs substructure, it's very easy to implement it inside the Monte Carlo from the matrix element. So it's the way that we do it.
Yeah, I remember this formula, but the Fs are all electromagnetic here.
Yes, yes.
Yeah,
so this is basically, that's why, yeah, we have gamma-gamma. Sorry, yeah?
How does the C boson come in? That was the question.
So this is, it's not the same Lagrangian. This one is only for the photon, of course. I didn't put the Lagrangian for the Z boson, but it's another implementation. When you have these events, where is it? Yes, here it is. Of course, it's not the same Lagrangian. What I showed you is just the Lagrangian for the 2 photons in the final state. But what we implemented is all of them, gamma-gamma, gamma-Z, ZZ, WW, and no TT bar. Also now we are doing the TD bar part for the anomalous coupling. So these all different channels inside the Monte Carlo. They are implemented independently.
Okay, thank you.
thank you very much again to Christophe for this talk. And we move on to the next talk, which is...
So we stop sharing. Yeah.
Please. By Tripathi, Sushanta from the Institute of Nuclear Science. Are you there?
Hi, can you hear me?
Yes, yes, we can hear you.
Okay, let me share slides. Okay, so I guess you can see the slides. Okay, so let me begin. Hello everyone, I'm Sushant Tripathi from ICN UNAM. So on behalf of Alice collaboration, I would present the topological studies of light flow hadron production in small collision systems with Alice at the LSC. So the major part of this, the results I will show is from ICN. So as an outline, I will start with a brief motivation, and then I will show the event shape observables like transverse velocity and relative transverse activity classifier. Then I will show the results for light flavor hadron production as a function of event shape observables. And then in this framework, we'll look for the jet quenching effects in small collision systems. And then finally, I will summarize my talk. So you might know that the recent measurements at the LSC have revealed that small collision systems exhibit collective-like behavior. And these behaviors were formerly thought to be achievable only in heavy ion collisions, where the data support the formation of QCP. So these behaviors are like the straightness enhancement in high multiplicity P and P-led collisions, and they are very similar to the lead-led ones. And we observe the similar features of baryon to meson ratios like P by pi and lambda by k short in PP, P-led, and lead-led collisions in low and high multiplicity classes. And also we observe a restructure in high multiplicity PP collisions. And all these features are expected to be formed in heavy ion collisions, but we still observe it in high multiplicity PP collisions. So we know that the small collision systems are traditionally used as a baseline for the study of possible formation of QCP in heavy ion collisions. So the formation, this origin of these collective like behaviors in small systems are still unclear. So for this reason, let us discuss two topics in this talk. The first one is isolating different physics regime. So with the help of event shape observables, we will disentangle the soft and hard processes. And then the obtained results from the data, we will compare it with the microscopic and macroscopic models like PTI and post-LSC. So for this, I will discuss the following multidifferential measurements, like the identify particle production as a function of transverse velocity in high multiplicity PP collisions, and then the charge particle and identify charge particle production as a function of relative transverse activity classifier. And in this framework, we will look for the jet quenching effects in small collision systems. So before showing the results, I will briefly explain the ALICE detector. So ALICE in LSC has collected data for PP, P-led, xenon, and lead collisions at several center of mass energies. The analysis which will be shown in this talk uses 4 detector subsystems. So those are like the inner tracking system, which is used for trigger tracking at vertex purpose, and it is also used for the multiplicity estimation. And in ALICE terminology, we call it as CL1 estimator. And then we take the help of time projection chamber for tracking and particle identification. And the time of flight detector is also used for the particle identification. And then we take the help of 2 forward detectors, V0A and V0C, which is used for trigger, and it is also used for the multiplicity estimation. And in ALICE terminology, we call it as V0M estimation. So the transverse velocity analysis, which I will show in next slides, will include the results from both V0M and CL1 estimation. And so the particle production using CL1 estimator is more sensitive to autocorrelations because we will measure the particles in the mid rapidity, and the estimator is in same rapidity region. However, the slicing the events based on V0M and measure the particle production in mid rapidity is more robust against the autocorrelations. So keeping this in mind, let us move to the results part. So the first part is looking at the identified particle production as a function of transverse velocity. So you might know that the transfer sphericity is a event shape observable, which has the capability to discriminate events based on hard and soft processes. So if we have sphericity tending to 0, then we call it as a jet events, and we expect the back-to-back structure. And if we have sphericity tending to 1, then we call it as isotropic events. So when you look at the azimuthal correlation plot as a function of different sphericity classes in PP collisions, we observe that at 0 to 10% sphericity class, we clearly see a peak in near and away side in simulation, PTR simulation. And when you go towards the 90 to 100% sphericity class, we observe enhanced underlying events, which is an indication of a soft QCD. Then let us look at the data, mean PT of the charged particles as a function of DNSAR data for PP13TV. So here we observe that the mean PT for jet events are higher compared to the mean PT of the isotropic events. So these plots indicates that sphericity has a very nice capability to discriminate the hard and soft processes. So the main aim is to look for the the results of the identified particles as a function of sphericity. So what we observe is that the sphericity estimator affects neutral and charged particle charge hadrons differently. So that's why to bring everything in similar footing, so we had to modify the sphericity calculation, and we have taken only the angular component of PT for the calculation sphericity, and we call it as unweighted transfer sphericity. So with this, I will show the results for the PT spectra of different particles like pion, kaon, and proton is shown here. So here in the upper plots, we have the PT spectra for isotropic, jetty, and sphericity integrated events. And the lower panel is basically the ratio of the isotropic and jetty ones to the sphericity integrated one. So as you can see that in all the plots of pion, kaon, and protons, we have clear dependence of the PT spectra on sphericity. And as you can see that at low PT, the isotropic events dominate, the particle production of the isotropic events dominate, and then after certain PT bin, we have the particle productions from jet events dominate, and we have distinct crossing points. And also we have the results for phi meson and xi as well. So here we have limited PT range till which we could measure the particle. So here we observe that we could not observe any distinct crossing point in the measured PT range for phi, and but we can see that it is approaching to unity. And for the xi, yeah, for xi, the results from isotropic and jet events are pretty much flat around unity. So let us see how it looks in CL1 estimator. So you can clearly see that I'm just going to the previous slide and the next slide. So here you can clearly see that in the CL1 estimator, the jet events dominate even at very lower PT bin, and for all pion, kaon, and protons. But for phi, we do not observe any kind of sphericity dependence at all. And for the case of xi, we in the previous case it was flat around unity, but here we nearly see a convergence to unity for both isotropic and jet events. So what we observe from the two comparison of the results is that V0M triggered events trigger isotropic and jet events have large multiplicity difference, while the CL1 triggered events disentangle the soft and hard processes more accurately in very small multiplicity. So for this reason, we will also look at the particle ratios as a function of sphericity. So here we have the particle ratios of K by pi and P by pi ratios. Similarly, we have the ratios in the upper panels, and we have the double ratio to sphericity integrated in the lower panel. And what we observe is that the ratio to pions show a very general trend of softening and hardening of the isotropic and jetty events. We have also the results for phi by pi and xi over pi ratio. So as we observe in the PT spectra, we do not observe any kind of sphericity dependence for phi by pi ratio. However, when xi by pi ratio and K by pi ratio, from both these plots, we get an indication that one can really enhance or suppress the strainness enhancement by selecting on the transfer sphericity. And in all these plots, we have the comparison with models like PTI and EPOS LSC. What we observe is the particle ratios are not reproduced by the models, but the double ratios are quite accurately reproduced by both the models, PTI and EPOS LSC. So let's go to the next part. Here we will show the identify particle production as a function of a relative transverse activity classifier. So this relative transverse activity classifier is another event shape observable, which is nothing but the charge particle multiplicity in the transverse region divided by the average charge particle multiplicity in the transverse region. So using RT, one can really vary the magnitude of the underlying events and study the particle production. So in RT tending to 0, this means that we have very less underlying events, and it is in an indication that I mean, we expect that the RT tends to 0, so the results should match the Jetty-like events based on transverse velocity. So it is a useful tool to look for the collective effects in varying the underlying events. And if you look at this plot, the average number of MPI as a function of RT, we observe that the increase of number of multiparticle interactions as a function of RT. So indeed, with the help of RT, we can look at the events as a function of varying multiparticle interactions. And of course, as it is an event observable, we can look for the interplay between soft and hard interactions. And the measurement at the transverse region will also give an insight to the autocorrelation effects. So the calculation of RT requires a leading particle. So to get the leading particle, we have to ensure that ensure a hard process. And if you look at this plot, we have the number density as a function of PT leading. So in the transverse region, after 5 J per C, we have nearly the same number density across different PT leading values. So for this reason, we have taken for the identified particle analysis, the PT leading greater than 5 G per C is used to get the I mean, to ensure the hard processes. So for the unidentified charge particle, we have used a hard cut of 8 to 15 G per C, because the fact that in this particular PT leading cut, we will look for the jet quenching effects, because the fact that this particular hard cut reduces the flow effects quite significantly. So with this, let us look at the particle ratios of the identified particle ratios as a function of RT. So here we have the P wave pi ratio for transverse and the toward region. So here are the results for two RT bins, one 0 to 0.5 and 2.5 to 5. So let me remind you that 0 to 0.5 have very less underlying events compared to the
5 minutes.
Yeah, thank you. So 2.5 to 5. So here in these plots, we observe a radial flow-like features in both the cases. And we have also the results for xi over pi ratio. So here also we get the similar trend for both the region. And in general, for the xi pi ratio, the EPOS LSC does a better job compared to the PTI. So the conclusion from this plot is like this ratio suggests that we still have the radial flow-like feature in PP, and it seems to be produced from the interplay between jet and underlying event components. So to extend this analysis, we had also looked at system side dependence of the particle production as a function of RT. So these are pretty new results, which were presented recently concluded Hartford's conference. And in this framework, we will look for the jet quenching effects. So here we have the charge particle production as a function of RT in PP and P-led collisions in different topological regions. So like near, away, and transverse side. So if you look at the transverse side, we have the PT spectra and the ratio to the 0 to 5 RTs PT spectra. And we observe that in the transverse side, with increase in RT, we have rise in the PT spectra in the lower panels in both the cases of PP and P-led. But this rise is less steeper in the P-led collisions. And for the case of near and away side, we observe that at high PT, the yields are nearly independent. But for at low PT, the yields are dependent on the RT, and it is more dependent on P-led collisions. So in all these plots, we have also compared the results with PTI 8 and EPOS LSC. And what we observe is both the models qualitatively explain the data. However, there is significant quantitative disagreement, and this data will help in tuning the MC models. So then we have also calculated the mean PT for different collision systems and in different topological regions. So here we have the mean PT from the near side. What we observe is at low RT, we have a bit of decrease in mean PT, and it becomes nearly flat after a certain RT bin. And similarly is the case for AV side. And for the transfer side, we observe an increase in mean PT with increase in RT. So when we put everything in same plot, what we observe is in the near and AV side, the mean PT decreases with increase in RT and reaches up to the value of the mean PT in the transfer side. This can be understood the fact that in both the near and AV side, we have also the contribution from the underlying events. So with this, let us move to the search for jet quenching effects in small collision systems. So for this purpose, we have taken the help of IPP, IP-led, and LED-led observable. This is nothing but the yield in these collision systems and subtracted, I mean, in near side and away side, subtracted to the transfer side. And it is scaled with the same thing in the PP minimum bias collisions. So in the left side, you see the plot for near side, and the right hand side, you see the plot for the away side. So if we observe any kind of suppression in the away side of this observable, this would be an indication of jet quenching effects in such collision systems. So indeed, we observe suppression of IV lead in central lead collisions. And this could be an indication of jet quenching, presence of jet quenching in central lead collisions. However, when we look for the small collision systems like PP and PLED in the limited N-charge transverse interval, we do not observe any kind of suppression at all. So this could be an indication of that there is no hint of jet quenching in the small collision systems. So in the recent paper, we had also looked for the IPP results from Pythia, Monastune. So here we observe that when the events events are subtracted from the underlying events. So in the case of UV subtracted ones, we observe that the IPP is consistent to 1, and it is they are consistent to 1 within 5%. And so this, as we know that by default, IPP, the PTR doesn't include the jet quenching. So comparing the results from data and with Pythia, we can conclude that there is no hint of jet quenching in small collision systems. So with this, I will summarize my talk. So I just saw that in the transfer sphericity and relative transfer security classifier can do very nice job in distinguishing jetty and isotropic events. The comparison of all the results with the models like PTI8 and EPOS-LSC will help to constrain the models. And in contrast to lead-lead collisions, we do not observe any hint of jet quenching in small collision systems. So thank you very much for your attention.
So thank you very much to Sushanta for this nice talk. And do we have any question?
I don't see any question up to now on YouTube. No questions. No questions in Zoom also.
So last chance for questions. So, no, then if there is no questions, since we are running out of time, we thank again Sushanta for this talk.
Thank you very much. Yeah.
Yes, and we move on to the next talk by Cecilia Uribe from WAP. Cecilia, are you ready?
Yes, I'm ready. Can you hear me?
Yes, thank you.
Perfect. Okay, so can I start sharing the talk or?
Yes, please.
Okay, thank you.
You're welcome.
Can you see my screen for my talk?
Yes.
Okay, perfect. So good day, everyone. Thank you for the invitation. So today I'm going to talk about the MRPC detectors for ultra-high rate applications. So future experiments are, as you have seen in different talks here during this meeting, are moving towards the high luminosity regime in order for access to rare events, such processes like BDKs or exotic charmonium resonances, for example. So in this scenario, the high rate capability is a key requirement for the detectors, together with excellent timing resolution for precise event reconstruction. So because of this, the multi-gap resistive plate chambers, or MRPCs, that have a very good timing performance are really used in high energy physics and nuclear experiments. So I'm not going to talk about the CMS RPCs here, but actually, as you can see, and Jose as well in his talk mentioned the muon detectors in the CMS experiment, which uses in the barrel and in the end cap these RPC detectors. Those are made of bakelite, and so are double gap RPCs. Today, I'm not going to talk about these detectors, but I'm going to talk about other detectors made of glass. And so I want to give you an example of, for the compressed baryonic matter, or CBM experiment, which is planned to operate at the Facility for Antiproton and Ion Research, which is called FAIR, in Germany, to study nucleus-nucleus collisions. So this experiment actually is planning to use the MRPCs for the time-of-flight system. And so these detectors need to withstand very harsh conditions, very high fluxes, going from 1 to 10 kilohertz per square centimeter for the outer region, and 10 to 25 kilohertz per square centimeter for the central region. So as you can see, there is an urgent necessity for these detectors to withstand very high fluxes and work with very good efficiencies to identify particles, and to be able, obviously, to reconstruct the trajectories of particles at higher momenta. So it would be nice then to produce these detectors that are robust and that can actually achieve time resolutions, for example, why not around 20 picoseconds. So as I said, these detectors are made of different materials, bakelite, ceramics, or even glass. That is the detectors that I'm going to talk about here. And so in this case, it's important to have a lower resistivity materials, because this would improve the rate capability of these MRPCs. Then, there is always a price to pay, right? So if low resistivity materials usually are thicker, so greater than 0.7 millimeters, compared to commercial soda lime glass, that is the most common, and this could go down to 0.28 millimeters. So then if we want to use a low resistive material, so in principle, we will have a thicker material, which could increase the material budget, that can impose limits on the number of gaps, which is bad, because we have actually seen that if we increase the number of gaps, actually we can improve the time resolution. And so then if we limit the number of gaps, obviously it will be more challenging to have high precision timing. Additionally, we want to maintain the feasibility to build large area detectors together with low cost, easy construction, and to have very robust detectors with a minimum material budget. So as you can see, we need different requirements. So We want robust detectors that perform very well to very high fluxes and that give us a very high precision time. So we're asking a lot. This is our wish list, but happily, it's possible actually to get these high rate and high timing detectors. And for that, we have been using a new low resistivity float glass coming from the company Picotech. And we have produced several actually detectors using this glass. And the good properties, some of the good properties about this glass is that the panes are made with a big area of more than 1 square meter and a thickness of around 400 microns. And we don't need actually to polish the surface because it has a very good quality. And the other thing is that it has a very good mechanical strength that can allow us to construct these robust detectors. So using this low resistive float glass, we have been building different detectors at CERN. And so we produced one of them with 6 gaps. And so we tested this detector in the PST10 at CERN. And we find an efficiency of 90% at 90 kilohertz per square centimeter. This is actually very good already, but obviously, as we would like to have higher rate fluxes, so we move our test to Germany, to the Elbe facility. And for that, we constructed another detector with 10 gap. And so in this facility, we can have fluxes up to 200 kilohertz per square centimeter, which actually is very good because it's going to allow us to prove the robustness of this detector under those harsh conditions. We as well measure the bulk resistivity of this glass in Germany. And so we produce results with these measurements that were published in a paper together with what I'm going to show you here. And I'll give you the reference at the end of my talk. Okay, so we move now to the MRPC construction. So as you can see here, basically, we have a single stock, as you can see. So we have here all these glass low resistivity. So we have basically 9 sheets here that are 0.4 millimeters thick. And then we have this outer glass here that compose the chamber. And then we have 2 PCBs or printed circuit boards here on top and one in bottom. We have as well pickup pads to collect obviously the signals that are going to be produced when the charged particles cross our detector. And then to produce these very small gaps, we are using a fishing line that has 0.16 millimeters diameter. That is actually what makes this the size of these gaps. And so in order as well to hold all these chamber together, we are using as well a honeycomb aramid fiber of 10 millimeters. And so we use some mylar as well between the printed board and these pickup pads in order to isolate the high voltage. So all this actually is put inside a aluminum box that is very well is completely sealed. So in order that the gas that this chamber uses don't escape the chamber, obviously, because the gas is going to help us to produce the ionization of the particles inside the chamber that at the end is going to give us the signals of these detectors. So it's obviously very important that we keep all these detectors sealed inside a box that is not actually presented here. By the way, if you want to understand the details that are very interesting inside the chamber, I recommend you to check the video by my student Manuel Alejandro del Rio Viera in this meeting. And he talks very nicely about all the physical processes that happens with the ionization inside these chambers, and then how the electric field is actually modified because of this chamber and the avalanches that are produced inside of these gaps. So the other thing that is very important as well inside these detectors is the gas mixture. So we are using a gas mixture of the commercially known Freon, that is we have 95%, and we have a 5% SF6 gas. And the mixture of gases inside of these detectors are very crucial as well for the features of the detectors. And for example, efficiency and the working point voltage, for example, where we can run our detector. So I recommend you as well to watch a video by the student Dalia Ramirez, that is a student of Salvador Carrillo from Ibero. So there are several groups, including Ibero, that are actually studying different gas mixtures, for example, for not just for CMS, but for Atlas and other experiments in the LHC. Because, sorry?
10 minutes, sorry.
Okay. So it's important because CERN wants to use green gases that are friendly to the environment. And so we have this run, obviously, to try to see what gas is more friendly to the environment, but still give us the right features that we need in our detectors. So we have these arrays of 4x4 square centimeters that are composed of 1 x 1 square centimeter. These are pads that actually are going to read basically the differential signal from top and bottom, and are going to be paired and sent to the NINO-ASIC. So this gas is run 30 millimeters per minute inside the chamber. So then in order to perform all these high rate studies, we take our detectors to this radiation source called ELBE, that stands for electron linac for beams with high brilliance and low emittance. So as you can see, we have different secondary beams, and we have a lot of different places here to run different experiments, from high energy physics to medical physics and biology. So we are here in this area that is called the radiation physics, is where we put our detector. And here are actually some of the features of this beam. And some of the important features for us, for example, is that we can have rays from 1 hertz to 1 megahertz, and the spot size is greater or equal to 10 square centimeters. So we are, which is nice, because then we can put the active area of our detector in this beam. And so we can actually run these studies that we need of high rate. So basically we are using single electrons with an energy of around 30 MeVs, even obviously when we can have different other energies thanks to this source, but we're using these 30 MeVs. And we have as well a pulse repetition frequency that is tunable actually, and a pulse duration of 5 picoseconds. And then we use as well the RF reference time jitter that arrives in this cavern as around 35 picoseconds. So here we can see the detector setup top view. And actually here we can see as well a picture actually of our detector. So we have identified it here. And we can see as well here different scintillators and that are connected to photomultipliers. So we are flushing, as I said, the gas mixture here inside of our detector. So I don't have a lot of time to go into details, but so basically we have, for example, these two sets of scintillators, S1, S2, S3, S4. And so what we do is that these are read out by the photomultiplier tubes. And then all sets are aligned with respect to the beam line and define a small 2 × 2 square centimeter area of the beam to provide a trigger signal. So basically, by measuring the number of coincidences of scintillator sets during the spill, we can monitor the instantaneous flux of particles that go through our detector. So the MRPC obviously is aligned with the beam. So we center it in the active area of the chamber to have obviously the beam spot in this area. So very well. So what we have here is that, as I said, all the MRPC differential signals are going to be sent to our data acquisition system that consists in the nanoASIC discriminator that is going to send another signal to the LVDS to NIM converter, and then is going to be read out by this web catcher. So this web catcher opens an acquisition window with a trigger for the PMT's logic signal when this is valid. And in our analysis, basically, if all the PMTs register a valid time, this event is regarded as a valid event. So then we can define the efficiency as the total number of the hits in the RPC, and then divided by the total number of events.
5 minutes.
Okay, so then for the time resolution, we have the full width and have maximum. We use that because we have a signal that is behaves as a Gaussian, so we can use this to compute the time resolution. And I'm going to show you this signal later on. So I'm going to move, as I don't have a lot of time, I'm going to move now to the results that we got actually. So basically for the studies of the ray capability, we see here the efficiency versus the different voltages that we applied to the chambers. So we started using a low flux of 2 kilohertz per square centimeter in our detector. And as we can see, obviously the efficiency increases when the voltage increases. And so for a 19.6 kilovolt point, we have basically a 97% efficiency, and is when actually we reach the plateau. We have here as well the efficiency versus the fluxes. So we are taking a window of 2 hertz per square centimeter to 200 hertz per square centimeter. And as we can see, this is with a voltage of 19.6 kilovolts in our chamber. We see actually that the efficiency, as you can see here, is basically greater or equal to 97%, even at a very high rate of 25 kilohertz per square centimeter. Then we see that the efficiency starts decreasing, but even so, we have a very good efficiency value of around 95%, even for very high fluxes of 200 kilohertz per square centimeter. So there is a time slewing dependency on the input signal amplitude, since the Nino chip is set at a fixed threshold for the MRPC signal discrimination. So we need to apply slewing correction by using the pulse width or the time over threshold information. So this is an example. So we are using here the time difference between our RPC and the time reference, and then we use a 19.2 kilovolts with a beam flux of 2 kilohertz per square centimeter, and we were able to obtain a time resolution of 36 picoseconds. So moving on, I'm going to talk now about the time resolution in terms of the high voltage and in terms of the fluxes. So following this correction technique, we obtain this different resolution using different voltages. So as you can see here, the voltage, when the voltage increases from 70.8 to 19.6 kilovolts, the time resolution actually improves, as can be seen here. So you see that, for example, for this RPC, from 18.5 to 19.6, we have time resolution actually very good, below of 40 picoseconds. So then this figure here shows us the time resolution versus the fluxes. Again, the window that we are taking is from 2 to 200 kilohertz per square centimeter. And so we can see that there is a degradation of the time resolution from 37 picoseconds to about 60 picoseconds when we reach the maximum flux. But even so, we still managed to have 50 picoseconds even at 50 resolution picosecond at fluxes less or equal to 100 kilohertz per square centimeter, which is very good. So to summarize all that I have been telling you, we use a single electron continuous wave beam of 30 MEVs at ELBE. We use a time jitter of 35 picoseconds. So we have a beam spot of size of greater or equal of 10 square centimeters, and a readout path size is about 16 square centimeters. So these features allow us to measure in very harsh conditions the features of our chambers. And what we have found is that the efficiency actually is quite good, even in these windows from 2 to 200 kilohertz per square centimeter. And the time resolution goes from 36 picoseconds with 2 kilohertz per square centimeter to 60 picoseconds at 200. So because we didn't have enough time in the test beam, we didn't really accumulate a lot of charge in our RPC. So basically we just had about 10 millicoulombs. So, but we are planning obviously to return with other detectors and with this detector to continue our test. Unfortunately, due to the COVID, we couldn't go in the spring of this year, but we still have plans to go. And then I just mentioned again that the resistivity studies are included in the related article that where I present all these results and more. So here it is, if you want to see it. And I just want to say then that actually for the CBM with these very high rates, so these RPCs actually could be quite good, because the maximum fluxes there would be around 25 kilohertz, and they want a better resolution of 100 picoseconds, which actually we achieve not only for these low rates, but even for high rates, we achieve a very good time resolution. So here is basically the people working in these experiments, people from CERN, from Germany, from BUAV, and from South Korea, from Mexico, obviously. And this is the article that I have been talking about. And so I want to thank you for your attention. And I leave you here with a picture of some of the members of the team in the ELBE facility during the test beam. So thank you very much.
Thank you, Cecilia, for this very interesting talk. Are there questions?
No, I don't see. Yes, Jose Benitez.
Yeah, Cecilia.
Yes.
So this is very nice. Very precise timing. Maybe I missed it, but why this experiment needs this kind of resolution?
Well, yeah, don't worry. At the beginning, I explained that actually this experiment is actually planning to use for the time of flight system, is planning to use this kind of detectors. So, but as you can see here, so they are going to use a wall that actually has basically around 100 square meters in total. So they are planning, this is a fixed target detector. And so, so the maximum fluxes that they are planning to use is around 25 kilohertz per square centimeter. And so the resolution that they are expecting is around 100 picoseconds, right? For to measure the particle drift time with this resolution. So basically, these efforts are mainly directed to accomplish what the CBM time of flight system needs. But as you can see, actually, we are trying to go even further. And this is because, as you mentioned in your talk, so with the high luminosity experiments, not just for the CBM, but for other experiments in the LHC. We need to have more robust detectors that can withstand these harsh conditions and high fluxes. So basically our effort is towards obviously mainly this experiment, but can be used for other applications and other experiments if others are interested.
So basically you want to measure this compressed baryonic matter. You want to measure its flight, basically, I think. Huh?
Yes, exactly. So they want to have, as I said, they are going to have this detector that is going to be located 10 meters behind the target. And so that's the reason why they should measure the particle drift time with better resolution of 100 picoseconds.
Okay. Okay. If there are no other questions, I could ask another one.
A very fast one, please.
Cecilia, for the CMS RPCs in the forward, do we also have this kind of timing resolution?
No, actually, so as you explained in your talk as well, the detectors that we use in CMS have a resolution about 1 nanosecond, but the improved RPCs obviously are more robust detectors that I just explained are going to be in an area that is going to have more background. And so they need obviously as well, so they need to be more robust. So we are building these detectors to be more robust, to stand higher fluxes. And actually we are going to improve the resolution, but not to this level of picoseconds, because we don't need it, right? I mean, it doesn't mean that you are going to put these time resolution detectors everywhere. It means that you are going to use what you need for every experiment that you require, right? So
I mean, it can help in the matching of the tracks. But anyway, it's fun.
Yeah, actually, yeah, that's actually a very good point. In principle, yes. I mean, you can use these detectors. At CMS, we are using them basically just for the tracking as a trigger, but we use it as in parallel with the other detectors that CSC and GTs that are in the CMS muon detector. But certainly, yes, I mean, this detector could be used for other purposes as well, for even more timing precision and resolution, of course, yes.
Thank you.
Sure.
Okay, thank you very much to Cecilia again. It's very encouraging. All these results are very encouraging. So we must move on because we are running out of time already. So the next talk is by Jade Olivas. Are you around, Jade?
Yes, here I am.
Yes, okay. Can you please share your...
Can you see the presentation?
Yes, and we can also hear you.
Okay. So first of all, I would like to thank to the organizers for giving me the opportunity to present this work here. I'm going to tell you about holography, quantum information, and gravity. This is a work in collaboration with my advisor, Alberto Guijosa. First, let me start with the ADS-CFT correspondence. This is a duality that puts in equivalence two distinct physical theories. On one side, we have the QFT without gravity, and on the other, we have a quantum theory of gravity. Of course, there is a dictionary which translates physical observables from one side to the other. But unfortunately, we don't have a rigorous proof of this statement. It is just a conjecture based on a lot of evidence from specific samples in certain limits. More precisely, what we want to say is that any conformal field theory is equivalent to a theory of quantum gravity on a given background. This statement is attributed to Maldacena, Gobser, Klebanov, and Witten. Let me describe for you each side of the corresponders. In the gravity side, we have the Einstein de Sitter space, which is a solution of Einstein equations with negative cosmological constant. In a given set of coordinates, the line element takes this form. And the diagram that describes the whole space-time geometry is this one. There is a characteristic manifold in this space-time, and is this red region, which is the boundary of the space-time. And let me just describe to you what a conformal field theory is. This is nothing more than a QFT that, in addition to being Poincare invariant, it is also invariant under rescalings. This CFT is defined on this red manifold, so we would like to refer to this as the boundary. Of course, we have an example of this correspondence, and is the Maldacenas example. It is the most studied and cited example of the duality, and it was found in 1997. He said that 4-dimensional super-Young mills, it's equivalent to type 2B string theory on ADS phi crosses phi. A piece of the dictionary says that any gauge invariant operator is dual to a matter field on the gravity side. And we have a prescription to compute correlators of gauge invariant operators. We just identify the string partition function with fields satisfying some sets of boundary conditions J. And these boundary conditions are going to be the sources of the field that we want to calculate the operators. And the lesson that we have to learn here is that CFT correlators can be calculated by partial functional differentiation with respect to the boundary conditions. Things get interesting when we take the following limits. In the string theory side, when we take the weakly curved regime and the weakly couple in the string coupling, this is equivalent to the strongly coupled regime in the CFT, and it's equivalent also to a CFT with many degrees of freedom. In these limits, the string partition function simplifies a lot, and we can approximate it by the saddle point approximation of type 2P supergravity. The lesson that we have to learn here is that semi-classical gravity give us access to the strongly coupled regime on the CFT side, and phi classical is a solution of type 2B supergravity equations of motion with given boundary conditions J. So now it's time to talk about quantum information. And to do that, let me just say something about quantum entanglement. This is a property of a system with at least two components. Also, it's a property that characterizes separable from non-separable states. And the best way to describe quantum entanglement is with this phrase that says that the best possible knowledge of the whole does not necessarily include the best possible knowledge of its parts. And to exemplify this, let me just assume the following. Imagine that Alice and Bob each have access to a spin 1 system, and the combination of the system is in this state. From Alice's perspective, she only has access to one part of the system, so she can only do measurements in this part. Since she doesn't know anything about Bob's system, she has to sum over all the possibilities of Bob's system. Then she finds that she has to describe her system with a mixed density matrix. So we started with a pure state that we ended up with a mixed density matrix. So is there a possibility to quantify quantum entanglement in a two-component system? And the answer is yes. This is always possible for a system that admits a separation of its degrees of freedom in two parts, one part related to A and one part related to B. In that sense, we define the entanglement entropy of a subsystem A as the one-moment entropy of the reduced density matrix. The reduced density matrix is nothing more than the trace of the total density matrix of the system. And for example, in the previous case, we can calculate the entanglement entropy associated to this state. If you do the calculation, you obtain this quantity. But for example, if you change the state and put this one that is a separate state, you obtain automatically zero. In holography, we have a prescription to calculate entanglement entropy. For example, if you want to calculate entanglement entropy for this interval A, you have to find in the geometry an extremal surface that has minimal area. So you can compute the entanglement entropy just computing the area of this extremal surface. There are other mathematical subtleties that I'm not going to mention, but this essentially is what we call the Ryu-Takayanagi or Huen-Rangaman-Takayanagi formula. Another useful concept is entanglement of purification. And to introduce this concept, let me just define what a purification is. Given a mixed state described by a density matrix rho S, it is always possible to find a bigger system, this one, and a pure density matrix, this one, such that when we take the trace over the auxiliary degrees of freedom, we recover the original density matrix. In that sense, we can define the entanglement of purification. The mathematical definition, I think, is too technical. So let me explain to you with this drawing. We have a system that it's separated in regions A and B, and it is described by a mixed density matrix. Since we can purify this system by finding an auxiliary degrees of freedom A prime and B prime, we can calculate the entanglement entropy of the region A and A prime. Then, if you want to compute the entanglement of purification, you have to minimize over all possible purifications and over all possible bipartitions of the system. We have a prescription in the geometry to calculate the entanglement of purification. If you have the system AB separated in this form, you have to find the Ryu-Takayanagi surface associated to the whole system. And then you make the separation of the degrees of freedom A and A prime using this cross-sectional surface. And the way to compute the entanglement of purification is by finding the minimal surface, minimal in the area sense. This technique was provided by Takayanagi, Umemoto, Nguyen, Devakul, Halbash, Saletel, and Swingle. With this concept, we can introduce what we call the excise duality. As we saw in the previous slide, the optimization procedure introduced an additional set of degrees of freedom A prime and B prime. In the gravity description, we saw that these degrees of freedom are localized on the Ryu-Takayanagi surface, that is the dot line. So it is natural to conjecture that the optimal state is dual to the space-time geometry of the blue region. I mean, we have an state that only describes the blue region. So in this sense, we want to understand better the excise duality. So if we trace over the degrees of freedom A prime and B prime, we have to reproduce a density matrix to compute correlation functions. But the problem here is that if we want to use holography, we don't have the full geometry, because in the excise duality, we only have a portion of the geometry. So this question arises: how can we implement the reduced density matrix in this reduced geometry? And just to picture what I said, let me just say that if you want to calculate the expectation value of operators inserted inside A, you have normally you have to trace over the degrees of freedom A and B with the total density matrix. But since the operators are localized inside A, you can do the trace over the degrees of freedom of B, and you obtain a reduced density matrix. So in some sense, if you want to implement the reduced density matrix in some holographic setup, you have to reproduce the original correlators. The way we implement that to solve this problem is by using the holographic Wilsonian renormalization group. And the usual formalism said that if you have the partition function in terms of the functional integral in momentum space, you separate this integral into regions. One that takes into account the UV behavior and one that takes into account the low energy behavior of the theory. Then you integrate out the UV behavior and you obtain an effective action that gives you the correct behavior for the low energy physics. In holography, the UV degrees of freedom are related to, in the gravitational side, with a portion of the space-time that is closer to the boundary. So in this sense, integrating out momentum, UV degrees of freedom, it's equivalent to integrating out geometry in the geometric side. The precise ways to do the holographic computation is given in these 3 lines. I'm not going to enter into technical details, so let me just proceed. So the way we implement this in this context is by integrating out the geometry that is outside the entanglement wedge. This, of course, produces an effective action for the interior geometry. The implementation of it's very different from the usual Wilsonian approach. In this case, we are integrating out AR information in the CFT. As I said, this is related with UV information in the geometry. This effective action has the same information as the whole space. Therefore, we can reproduce the same correlators function, the same correlators as in the whole space. And with this, we mean that the implementation is by integrating out the geometry, we obtain a boundary term that describes correctly the geometry that is outside. So we get implementation of the reduced density metrics. Okay, let me just finish with the conclusions and future work. Entanglement is a very important tool to prove the geometry. Many important interesting results arise from the Ryu-Takayanagi surface, the Ryu-Takayanagi formula. It is worthwhile to explore other geometric realizations of entanglement measures. This can give us a better understanding of the geometry. The excise duality represents a self-contained subregion version of the usual holographic duality. There are other examples in this direction. One is ADS-BSCFT. Obviously, the next step is to calculate precisely correlation functions of operators inserted in A. And other work is related to causality conditions, metric degrees of freedom, and entanglement entropy. So thanks for your attention.
So thank you very much, Jake. We have some time for questions.
Mm-hmm. I don't see a questions on YouTube. Let's see if somebody, yes, Wolby.
Yes, thank you. I was just puzzling because in the beginning you said you're mapping the system to a low energy to a large energy system or weakly coupled system, and then you can deal with it with a saddle point approximation, which is basically classical. So if you're doing that, then I don't know how you want to keep track of all the interference effects that come in the quantum information. But in the final part, then you describe Wilson renormalization group. So this is how the quantum effects are you keep track of the quantum effects?
The quantum effect related to the UV information in the string theory side, you refer?
Yes, I mean, just if you talk about the quantum information, Alice and Bob and so on, you certainly need quantum effects, and the classical
but
saddle point approximation is not, I think, is not able to do that. So that is the question. How?
No, the saddle point approximation in the string theory side only gives you a way to compute correlators in the large N expansion. I mean, you can only compute correlators when the number of colors of the CFT or number of degrees of freedom is very big.
Yes, but this is essentially classical. You look for a minimum. Actually, it's not a saddle point.
It's classical in the string.
And you do not really incorporate the quantum fluctuations, right?
Yeah, but this is classical in the string side, but this gives you information about the quantum theory, and the quantum theory is not classical in this limit.
Yeah. Okay. Thank you.
Mm-hmm.
Okay. Are there more questions?
No, I don't see more questions.
No. So then we have the lunch time, the lunch break. We have around 1 hour and 10 minutes. So we will back at around 2:20. So thank you very much to everybody.
Thank you very much, Karen.
No, you're welcome.